Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the shimmering past and quiet possibilities of two very different worlds, one still blue and breathing, the other cold, rust-coloured and dry. We'll be asking a question that reaches back to the birth of planets and forward to the future of life itself. Where did Earth's water come from, and why did Mars lose theirs? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these gentle explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the ancient story of water. Let's start, not with oceans, but with canals. Not real ones, but imagined lines crisscrossing the surface of Mars through the lens of a telescope in the 19th century. It's a strange place to begin a tale about Earth's oceans, but a necessary one. Because sometimes, to understand what we have, we must first explore what others thought might be. In the late 1800s, a wealthy American astronomer named Percival Lowell peered through his telescope and believed he saw something astonishing on Mars. Long, straight lines, some hundreds of kilometres long, seemed to stitch across the surface. He called them canals, and in his mind, they were not just natural formations. No, these were the work of intelligent beings. Martians who had built a vast irrigation system to transport melting water from the polar ice caps to drier regions of the planet. Lowell's imagination filled in the gaps that science couldn't yet reach. He saw a dying planet desperately trying to hold on to its last drops of water. And to many at the time, it was a compelling vision. Books, debates, and newspaper illustrations followed. For a while, Mars seemed almost alive, a place of engineering, of intelligence, of thirst. But as science sharpened its instruments, the illusion dissolved. In the 1960s and 70s, NASA's Mariner missions flew by and photographed Mars close-up for the first time. What they found was not a planet of canals and civilizations, but a barren world. Cold, dusty and dry. The lines were real in a sense. Natural ridges, cracks and optical illusions, but the story behind them had evaporated like mist in the morning sun. Yet that longing, that quiet hope embedded in Lowell's dream didn't disappear. It simply changed direction. Because while Mars turned out to be dry and rust-red, Earth revealed itself more vividly than ever as the blue planet, a world wrapped in oceans dotted with lakes, cloaked in clouds and laced with rivers. Water is everywhere here. It dances in the sky, sleeps in glaciers, flows beneath our feet, and fills the air we breathe. It shapes coastlines and mountains. It cools, nourishes, and carves. It is the soft pulse behind every heartbeat, the mist on your window, the tear on a cheek. More than 70% of Earth's surface is covered in water, from the vastness of the Pacific Ocean to the tiniest droplets clinging to a leaf at dawn. This planet is rich with liquid life. But here's the deeper mystery. It wasn't always this way. Go far enough back in time, beyond continents, beyond fossils, before even the moon was born, and you reach a young Earth that wasn't wet at all. In fact, it was dry, hot and violent. 4.5 billion years ago, Earth formed from the dust and rocks circling a young sun. But it was born inside the snow line, a region too warm for ice to exist naturally. Which means, by all logic, Earth should have been a desert, a scorched rock in space, bone dry and barren. And yet, somehow it isn't. Somehow it has oceans. Somehow it has rain. So where did all the water come from? How did a planet formed in the sun's hot embrace end up with seas that stretch beyond the horizon? That's the mystery we're going to follow tonight. Softly, slowly, letting it unfold like ripples in a pond. And as we do, we'll return to Mars from time to time, because its story, though sadder, is no less important. If Earth is a symphony of water, Mars is the silence that follows a vanished note, a reminder of what might have been. So take a deep breath. Let your thoughts float. The story of water is vast and ancient, but we'll go one drop at a time. Let's stay with that image a moment longer. The early Earth, spinning beneath a pale young sun. There were no continents then, no oceans yet, only molten rock and vaporous skies. The planet was a furnace, its surface churning with magma, its atmosphere thick with carbon dioxide, nitrogen, and the sulphurous breath of volcanic outgassing. And still, no water to be seen. No rain, no rivers, no blue. It's almost unimaginable, isn't it, that this world, now so lush and saturated with liquid life, began as a hostile sphere of fire. And yet, if we could travel back in time, we wouldn't find a drop to drink. The Earth as we know it was forged inside a dry zone of the solar system, too close to the sun, too warm for water or ice to condense naturally. And so for the first tens of millions of years it spun on, parched and lonely. But while the Earth baked, elsewhere in the solar system, farther from the sun's scorching reach, a different story was forming. Beyond what scientists call the frost line, or snow line, where the sun's heat was weak enough for volatile substances like water, ammonia, and methane to freeze, countless bodies were taking shape. Asteroids, comets, and primitive planetesimals, each a frozen time capsule filled with the very ingredients Earth lacked. And some of those bodies, nudged by the invisible pull of gravity, began a long, slow migration inward. In the vast ballet of the early solar system, giant planets like Jupiter and Saturn didn't sit still. They moved, subtly and dramatically, their gravitational influence creating ripples and distortions in the paths of smaller objects. As Jupiter edged inward, even briefly it disturbed the asteroid belt, sending icy fragments hurtling toward the inner planets like cosmic messengers. Some crashed into the moon, others into Mars. Many, perhaps the luckiest, struck Earth. These were not gentle arrivals. Imagine an asteroid the size of a mountain slamming into a molten world. The heat, the shock waves, the chaos. And yet inside that violence was a gift. Water, locked within minerals and ice, vaporized upon impact, rising into the air, mixing with volcanic gases already escaping from Earth's core. Steam filled the skies. For thousands of years, maybe longer, Earth was wrapped in clouds, thick, brooding, and full of moisture. And then it rained. Not for hours, not for days, but for centuries. Rain fell in endless sheets over plains of cooling rock and craters still glowing red. The water had nowhere to go but down, collecting in low basins, pooling in valleys, carving channels as it moved. Over time, the Earth's first oceans were born, shallow at first, then vast. And as the planet cooled, the rain slowed, the clouds thinned, and the blue settled in. This image, of a world soaked slowly into life, is one of science's quiet wonders. There's no single moment you can point to and say, here is when the sea began. It wasn't. Like switching on a faucet. It was more like memory being written over eons, each drop a word, each river a sentence in the autobiography of a planet. And while this story unfolded here, on Earth, Mars was watching from across the cosmic street. Mars, smaller, cooler, with its own ancient lava plains and river valleys, was once wet too. That much we know. The dried out beds of rivers and the mineral fingerprints of water speak clearly of a past where liquid once danced across its surface. There may have been lakes, even shallow seas. Perhaps, for a brief cosmic moment, Mars was a watery sibling. But its time was short. Mars had two problems. First, it was small. That meant it couldn't hold on to its internal heat as long as Earth could. Without that heat, it lost its magnetic field early. And with no magnetic field to shield it, the planet's atmosphere began to leak away, atom by atom, stripped by solar wind like pages torn from a book. As the atmosphere thinned, surface pressure dropped, and with it the stability of liquid water. Rivers vanished, lakes froze, Oceans, if they ever truly formed, evaporated into the vacuum of space or were locked away underground as frozen relics. The second problem was timing. Mars may have had water, but it didn't have long enough to make it last. Whatever warmth it once held faded quickly. The planet became a desert, not just of sand, but of time arrested in its early chapters. And so today, we see only hints of what once was, dusty deltas, ghost rivers and ice beneath the surface, hidden like fossils of a forgotten rain. It's tempting to see Earth's water as inevitable, to think of oceans as a given. But Mars reminds us that water is not promised. It is a cosmic stroke of luck, a convergence of position, mass, timing and protection. Earth got just enough mass to hold its atmosphere, just the right distance to keep its surface temperate, just the right help, from Jupiter's chaos and ancient asteroid collisions, to bring the missing water home. As we begin to trace this long story, from the frost line to falling rain, from molten beginnings to global seas, let's carry with us that sense of quiet gratitude. The glass of water beside your bed, the soft rhythm of waves meeting shore, the rain on your window. These are not just everyday comforts. They are the echoes of a planetary history written in liquid and still unfolding every day. If you were drifting in the quiet darkness of space, far enough from home that continents and borders blurred to nothing, Earth would appear not as a map or a name, but as a delicate shimmering orb, deep blue with swirls of white and hints of browns and greens tucked beneath. It is not the colour of forests or deserts that would first catch your eye. It is the water, the oceans, the clouds, the rolling mist on morning hills. Water gives Earth its hue, its rhythm, and its heartbeat. This is our blue marble, and tonight we begin by simply marvelling at its most defining feature. Over 70% of Earth's surface is covered in water. It wraps around the planet like a soft, fluid skin, pooled in oceans and seas, gathered in lakes and rivers, stretched thin across marshes and wetlands, or suspended in the air as clouds and vapour. It drips from leaves, runs through soil, and fills the lungs of whales. It traces every crack of canyon and kisses every shore. Water is not just present here, it is pervasive, persistent and patiently powerful. And yet, for all its familiarity, water is never still. It is motion incarnate, always cycling, always whispering forward. It wears down mountains, not by force, but by patience. It carves valleys and deposits deltas. It shapes land with such quiet conviction that you almost forget the continents themselves were sculpted by its hands. Rivers draw their winding paths not from indecision, but from the earth's subtle slopes and the water's careful listening. Each trickle, each flood, each falling raindrop joins a longer journey. A journey that began long before humans arrived and will continue long after we are gone. Even the atmosphere carries this liquid legacy. Clouds that appear soft and weightless are in truth dense caravans of suspended droplets. They float above our cities and coastlines, but they are travellers, not residents. Pulled by winds, charged by sunlight, they gather and part, shading forests, crossing deserts, and eventually releasing their cargo as rain, snow, sleet or fog. This is how the sky returns water to the earth, not as a favour, but as part of a long-standing promise. What rises will fall, and what falls will rise again. And underneath the surface, in places you cannot see, water moves too. It trickles down through rock and soil, seeps into aquifers and ancient underground rivers, and rests in cool dark chambers for centuries or more. These hidden reservoirs act as the planet's quiet savings account tapped by tree roots, springs and wells. Even here in stillness, water waits for its call to rejoin the journey. But water is more than a traveller. It is a conductor, a messenger, a keeper of balance. It moderates Earth's climate in ways we often take for granted. Oceans absorb heat from the sun during the day and release it slowly through the night, acting like planetary blankets that soften the temperature swings between day and night, season and season. Without these vast bodies of water buffering the atmosphere, our world would veer into extremes, searing heat by day, bitter cold by night. Instead, we experience something else, seasons that cycle with grace, coastlines warmed by ocean currents, clouds that shield and nourish. This balancing act isn't only planetary, it's personal. Your body too is a blue planet in miniature. You're made mostly of water, cells bathed in it, blood carried by it, thoughts firing thanks to ions dissolved in it. Every breath you take evaporates a trace of it. Every movement, every beat of your heart depends on its fluid presence. Water flows through you just as it flows across plains and mountains, binding every living thing to every other in a soft web of wet connection. And maybe it's this very universality that makes water so poetic. A lake reflects the sky not just in colour, but in silence. A rainstorm is felt as much in mood as in moisture. Tears speak what words cannot. We do not merely observe water, we feel it, we trust it, we respond to it. In the scent of a coming storm, in the way our breath fogs on a cold morning, in the stillness that follows rain. For something so quiet, water speaks volumes. Tonight, as we begin to explore the mystery of its origin and the fragility of its presence, it helps to start by simply seeing it again. Not in passing, not as background, but as central, as the defining feature of our world. It's easy to forget what's always been there, to overlook the puddle, the tide, the fog on the mirror. But these are the signs of Earth's great gift, its liquid signature. Mars had valleys too once, and riverbeds, and clouds, but it couldn't hold on. Earth did. And part of what makes this story so rich, so full of quiet wonder, is not just that we have water, but that we still have it. That the rain continues, that the oceans breathe, that even in stillness water remembers how to move. So take a sip of water if there's some nearby. Let it rest on your tongue. It's older than you, older than cities, perhaps older than the mountains outside your window. This moment, simple, familiar, is part of something ancient. And that, more than anything, is what makes Earth a world apart, a world wrapped in water, a blue marble floating quietly in space. If Earth could exhale, it would do so in water. Not with the rush of wind, but with the soft drift of vapour, the quiet fall of rain, and the mist that rises from forest floors in the early morning. Water is Earth's breath, its sigh, its song, and like breath, it never truly ends. It only moves in circles. The water cycle is one of the oldest processes on the planet. It is continuous, elegant, and remarkably patient. It does not rush or ask for recognition. It simply happens over and over for millions of years. And because it is so constant, we often overlook just how extraordinary it really is. Let's begin where most of it does, with the sun warming the sea. Oceans absorb sunlight like giant solar panels. As the surface heats, water molecules gain energy and begin to escape into the air as vapour. This is evaporation. You've seen it on a summer sidewalk after rain, or rising gently from a kettle on the stove. But here, on a planetary scale, it becomes something vast. Thousands of cubic kilometres of water rise into the sky each year, invisible to the eye, lifting from oceans, lakes, rivers, and even damp leaves and soil. Plants, too, release water in a quiet exhale called transpiration. From the forest floor to the canopy above, leaves open microscopic pores to let go of moisture, and in doing so they help stitch green places into the cycle. High above, in the colder air, that vapour condenses. It gathers around tiny particles, dust, salt, pollen, and clings together to form droplets. This is condensation, the beginning of clouds. Wisps at first, then thicker bodies of mist, white or grey, floating miles above the surface. They are not light, despite their airy appearance. A single cloud can carry millions of gallons of water, suspended effortlessly, moved by wind, shaped by pressure, lit by sun and moonlight. Eventually the droplets within grow too heavy to stay aloft. Gravity pulls them down and the sky returns what it borrowed. Rain falls, or snow, or sleet, hail, drizzle, each a different expression of the same quiet promise that water will come back to earth. Precipitation may land on rock, on leaf, on rooftop, may rush into streams or sink into soil. It may freeze or puddle, or be drunk by a passing animal. But wherever it lands, it begins another part of the journey. Much of it flows over land, tracing the paths of least resistance. Tiny rivulets become creeks, creeks join into rivers, and rivers rush toward the sea. Along the way, water sculpts and nourishes, carries sediment, minerals, fallen leaves, and whispers of stories from upstream. But not all water runs along the surface. Some seeps into the ground, moving through layers of soil and stone into aquifers, ancient hidden lakes beneath our feet. There it may rest for centuries, or be pulled back into light by a tree root or a well, or a spring bubbling quietly from the earth. This is infiltration and groundwater flow, an invisible part of the cycle, but one just as important. And still the journey continues. From aquifer to spring, spring to stream, stream to river, river to sea, until once again the sun finds the surface and the water lifts back into air. There is no beginning or end, only motion. What makes the water cycle remarkable is not just its constancy, but its scale. A single molecule of water can spend a few days as vapour, then fall into a river, spend months flowing through a watershed, sink into soil for decades, freeze inside a glacier for centuries, and finally melt, evaporate, and begin again. The water you see outside your window might have once been inside a mountain, a tree, or a dinosaur. It may have fallen as rain on ancient soil, or been held in a cloud that drifted over forgotten landscapes. It is ancient but never old, it is always becoming. And yet for all its motion, the total amount of water on Earth remains nearly constant. The same water that has always been here is still here. We do not gain or lose it in large amounts. It is simply rearranged, recycled, remembered. There are even rivers in the sky, so-called atmospheric rivers, bands of concentrated moisture that stretch thousands of kilometres through the air, carrying more water than the Amazon. When they reach land, they can release astonishing amounts of rain or snow, shaping not just weather patterns, but whole ecosystems. We don't always notice them unless they turn violent, but they are there, flowing above us, silently echoing the rivers below. Then there are aquifers, subterranean reservoirs filled not by pipes or pumps, but by time. These hidden lakes, some millions of years old, are slow to fill and slow to forget. When we draw from them faster than they can replenish, the cycle is broken. And when it breaks, the consequences echo not in floods or storms, but in silence. Empty wells, parched fields, sinking ground. Water is patient for us, but not limitless. Still, despite these interruptions, the cycle persists. It has for nearly 4 billion years. Through mass extinctions, shifting continents, ice ages, and firestorms, water has moved, changed, and returned. The cycle is not delicate, it is resilient, and yet its elegance lies in how it touches everything, without rushing, without pride. Tonight, as you rest, that cycle continues. Outside your window, a cloud may be forming. Somewhere a drop of rain begins to fall, somewhere else sunlight is pulling vapour from the ocean surface. All around the world Earth is breathing, and that breath, quiet and rhythmic, is made of water. Among all the planets we know, scattered across the dark stretch of space, Earth is still the only one where water flows freely across the surface in its liquid form. This might seem unremarkable at first because it is so ordinary here. We take showers in it, we swim in it, we boil it for tea. It spills, evaporates, freezes, and returns. But if you were to visit Venus or Mercury, or even the icy moons of Jupiter, you would quickly realise just how special Earth's quiet puddles and lakes really are. Liquid water is a rarity in the cosmos, and on Earth it is everything. Water in its liquid state is the most versatile substance known to support life, not just because it is wet or because it feels familiar, but because of what it can do at the molecular level. It is the perfect medium for dissolving, carrying and reacting. It binds to other molecules easily. It holds heat, moderates temperature, and participates in chemical reactions with a kind of gentle elegance. These traits aren't just convenient, they're essential for life as we understand it. Inside every living cell, from the simplest microbe to the most complex animal, water is the stage upon which life plays out. DNA unwinds in its presence. Proteins fold into precise shapes because of how water surrounds them. Nutrients move between cells because they are dissolved in water-based fluids. Even the electrical impulses in your brain, those quiet sparks that form thoughts and memories, depend on the movement of ions, charged particles carried by water. Without liquid water, life as we know it would halt. But how does Earth manage to keep it in the golden, flowing state? The answer begins with where Earth is placed, positioned so precisely balanced that it's often called the Goldilocks zone. Not too close to the sun, where oceans would boil away, not too far where they would freeze into permanent silence. Earth sits just right. Its average temperature allows water to exist in all three states, solid, liquid, and gas, and to move freely between them. That freedom is what powers the water cycle, nourishes ecosystems, and allows life to adapt and thrive. However, position alone isn't enough. Other planets exist in similar orbits and show no signs of the wet abundance we experience here. What makes Earth different is how it holds on to that water. Several key ingredients combine in our planet's favour. First, Earth is large enough to maintain gravity strong enough to keep its atmosphere in place. Without that gravitational pull, water vapour would drift into space, lost forever, as it likely did on Mars. Second, Earth's internal heat, generated from its molten core, powers a magnetic field, a protective bubble that shields the atmosphere from the relentless battering of solar wind. This magnetic field acts like a planetary umbrella, deflecting charged particles that would otherwise strip away our air and water, molecule by molecule. Mars, again, offers a cautionary tale. A planet that cooled too quickly, lost its magnetic field, and watched helplessly as its sky and seas were taken by the sun. Third, Earth's atmosphere itself is thick enough to maintain pressure on the surface, allowing water to stay liquid rather than instantly boil or freeze. This balance of temperature and pressure is delicate. Tilt it too far in either direction, and water disappears or becomes inaccessible. But here, on this particular world, it has persisted, filling valleys and lowlands, moving through clouds and aquifers and soaking deep into the soil. It's worth pausing to consider just how tightly these conditions are interwoven. If Earth was slightly smaller, its atmosphere might have been thinner, and water would evaporate more easily. If it was slightly closer to the sun, surface temperatures could rise enough to disrupt the liquid state entirely. If it had formed without enough iron and nickel to generate a magnetic field, our air and oceans might have vanished into the void long ago. Instead, Earth ended up in a kind of planetary harmony, and that harmony allowed for complexity. With water flowing across the surface, the planet's rocks began to weather and erode. Nutrients were carried to the sea, minerals dissolved and reformed. The oceans became a great cauldron of chemistry, where life could begin. And once it did, water became the bloodstream of evolution. Fish navigated its currents, amphibians emerged from it, mammals drank from its banks. Even now, no organism escapes its pull. From towering redwoods to microscopic plankton, every life form speaks the language of water. And as life evolved, it didn't just use water, it helped shape how water moved. Plants began to regulate local humidity through transpiration. Beavers dammed rivers. Human civilizations rose along rivers, channeled rainwater, dug wells and redirected flows. We have always followed it, adapted to it, and relied on its presence. Our bodies are filled with it. Our stories are full of it. Our science is rooted in its properties. So while we might marvel at stars and galaxies, it's worth remembering that life here depends less on fire and more on the quiet persistence of liquid. It doesn't shine like the sun, but it nourishes like breath. And unlike other forces of nature, water does not conquer. It connects. It fills the spaces between things. It carries memory, temperature, nutrients and time. It whispers across the land rather than shouting, and in that whisper lies the story of everything we know. If liquid water is the lifeblood of our planet, then ice and vapour are its quiet companions, ever-present, often overlooked, but no less vital. They are water's alternate forms, its disguises, its soft extensions into the corners of the world. And though they may seem still or insubstantial, ice and vapour help hold the delicate balance that makes Earth not only habitable, but alive. Let's begin with ice, the solid state of water, frozen in time, sometimes for thousands or even millions of years. It sits patiently atop mountain tops and blankets the poles. It hangs from eaves in winter and gathers in ancient glaciers that move almost imperceptibly under their own weight. When you picture the Arctic or Antarctica, what you see is not just snow, but a frozen archive. Within each layer of compacted snow and ice lies a record of the past. Tiny bubbles of ancient atmosphere, particles from volcanic eruptions, pollen from long-gone forests. To study glacial ice is to read the diary of Earth's climate, written in layers, preserved in silence. But ice is not merely a record keeper. It also plays an active role in regulating the planet's temperature. White surfaces, like snow and ice, reflect sunlight back into space, a process known as the albedo effect. This reflectivity helps cool the Earth, keeping global temperatures within a narrow, livable range. When glaciers melt, dark ground or ocean is exposed beneath, which absorbs more heat, causing temperatures to rise further. It's a feedback loop, subtle and slow but powerful. Ice in its stillness helps Earth stay balanced. Lose too much of it, and the balance begins to shift. Then there are glaciers, not frozen statues but rivers of slow-moving ice that carve valleys and shape mountains. Over millennia they've gouged deep troughs, left behind moraines, and sculpted landscapes we now hike, photograph and inhabit. If you've ever stood in a U-shaped valley or by a lake with oddly scattered boulders, you've stood in the footprint of a glacier. These frozen rivers don't roar like waterfalls or churn like oceans, but they move with purpose, guided by gravity and time. Meanwhile, far above, water takes another form, one you can't touch but you can feel. Water vapour, though invisible, fills the air around you. It clings to your skin in humid air, curls into fog along coastal roads, and forms clouds that drift like dream shapes overhead. While it may not seem substantial, water vapour is, in fact, Earth's most abundant greenhouse gas. It traps heat, moderating the planet's energy balance, and amplifies the warming effects of other gases. It doesn't act alone, but it responds, growing more abundant as temperatures rise, and thinning out as they cool. It is this interplay between vapour, liquid and ice that creates weather, not as something external, but as the direct result of water transforming states. Clouds form when vapour condenses. Rain falls when droplets coalesce and grow too heavy to stay suspended. Snow emerges when temperatures dip below freezing in the upper atmosphere. Fog hugs the ground when warm air meets cold earth. Hail, sleet, dew, frost. Each is simply water, changing its costume to meet the moment. Even inside our homes we witness these shifts. A glass of cold water fogs on a warm day. A bathroom mirror steams after a hot shower. A kettle whistles as liquid becomes vapour, dancing visibly into the air. These are small signs, but they're everywhere. A reminder that water does not rest. It adapts. Clouds in particular are among water's most poetic forms. They drift, gather, darken and disappear, sometimes quietly, sometimes with drama. They offer shelter from the sun, signal coming storms and inspire daydreams. But behind their beauty lies complexity. Clouds influence temperature, block radiation, and redistribute moisture across continents. Some form high and wispy, others low and heavy. Some carry barely a trace of water, while others burst into life-giving storms. Yet all are born of the same humble vapour, and vapour has a way of wandering. A molecule of water evaporated from the Pacific may find itself falling as rain in the Andes. A droplet lifted from the Amazon canopy might one day descend onto an African plain. There are no borders in the sky, only patterns. Chaotic, yes, but also rhythmic. It's easier to forget this global journey as we look up at the clouds, but they are not merely overhead. They are in motion, carrying memories across the air. Ice and vapour, then, are more than opposites to the liquid we drink. They are partners in a dance, one slow and crystalline, the other fast and fleeting. One cools and stabilises, the other warms and stirs. Together they complete water's full story. Without vapour there is no rain, without ice no long-term storage, without either no weather, no climate, no balance. And so, while we often think of water as a river or an ocean, it may be more accurate to think of it as a shapeshifter. A traveller that takes many forms, each with its own voice, the creak of ice, the sigh of steam, the hush of snow falling in the dark. Tonight, as you sleep, clouds will drift across the world. Glaciers will groan ever so slightly as they shift. Somewhere frost will begin to bloom on a quiet field. And all of it, the freezing, the melting, the rising and the falling, is part of the same quiet miracle. The presence of water, in all its forms, whispering softly across the skin of this blue planet. Before there were oceans, before even the continents had names or shapes, there was only heat. Not the warmth of a summer afternoon or the dry crackle of a desert wind, but a deep, unrelenting heat that boiled from the core of a newborn planet. The early Earth, more than 4.5 billion years ago, was not a hospitable place. It was a sphere of fire and metal, still glowing from its violent birth, still reshaping itself with each collision and each volcanic breath. The surface was a shifting sea of magma, the sky thick with noxious gas and ash, and the stars above would have been barely visible through the dense, toxic haze. There was no blue, no clouds, no rivers to trace, and certainly no rain. It was, in every meaningful way, a world without water. This might be difficult to imagine now, living as we do surrounded by the quiet omnipresence of water, flowing from taps, soaking into soil, falling gently from the sky. But Earth's beginning was dry, scorched and chaotic, and not just because of its youth, but because of where it happened to form. Earth was born inside a region of the solar system too close to the sun for water to naturally condense. This region, known by planetary scientists as the snow line, marks the boundary beyond which it is cold enough in the solar nebula, the vast disk of gas and dust from which the planets emerged, for ice to form and remain stable. Within the snow line, the warmth of the young sun ensured that most volatile substances, like water, ammonia, and methane, existed only as gas, and gases are difficult for small rocky planets to hold on to. The building blocks of Earth were dry rocks, silicates and metals, and even if these minerals contained trace amounts of water locked within their crystalline structures, the heat and violence of early Earth made it nearly impossible for that moisture to persist on the surface. In its earliest eons, the Earth was constantly bombarded by space debris, comets, asteroids, planetesimals, remnants of the solar system's turbulent formation. Some of these impacts were minor, leaving behind craters or mixing new minerals into the molten crust. Others were more significant, planet-sized collisions that melted the entire surface, vaporized existing crust, and reset the clock on any progress towards stability. One such collision, occurring roughly 4.5 billion years ago, was so enormous that it may have created the Moon. A Mars-sized object, often referred to as Theia, is believed to have slammed into the proto-Earth with such force that it ejected material into orbit. That material eventually coalesced into the satellite that now lights our night skies, but the impact did more than give Earth a companion. It remixed the entire outer layer of the planet, possibly influencing its core formation, its rotation, and, importantly, its ability to hold on to volatile elements like water. Still, even after this cataclysmic event, the surface remained hot and dry for millions of years. Volcanic eruptions were common, pouring rivers of lava across the crust and belching gases into the thickening atmosphere. These gases were rich in carbon dioxide, nitrogen, sulfur compounds, and, crucially, water vapour. The heat from Earth's interior kept the crust in flux and the air unstable. There may have been short-lived pools of condensed water, rapidly evaporated by the sun or boiled away by eruptions. But no oceans, not yet. It is important to understand that while the Earth lacked surface water, it was not entirely devoid of water in all forms. Some minerals in the mantle, such as olivine and pyroxene, can trap small amounts of hydrogen and oxygen atoms within their structure. These bonded atoms form hydroxyl groups and under the right conditions can recombine to create water, but this water was locked away deep inside the planet, inaccessible and invisible. To become the water we know, the rivers and rains, the oceans and mist, it would need to be released. And that would take time and tectonics and a planetary process capable of lifting water from stone. This is where the mystery deepens. Because while the Earth was too hot, too dry, and too close to the sun to form oceans on its own, it somehow ended up with enough water to cover most of its surface, enough to support weather, climate, and life, enough to fill basins 5 miles deep and still lap gently at the edges. The question of how that happened, how a dry, molten world became a blue planet, is one of the most enduring questions in planetary science. It's not just about where water came from, it's about timing, chemistry, cosmic accidents, and geological persistence. And to answer it, scientists have had to look not just at Earth, but at comets, meteorites, asteroids, and the dusty remains of solar systems far from our own. They've had to analyse isotope ratios, simulate planetary collisions, and examine volcanic rocks that have never seen the open ski. In the next sessions, we'll explore the two leading theories. One says that Earth made its water from within, exhaling it slowly like breath through mountains and molten vents. The other says it came from beyond, carried here on icy stones from the outer solar system, delivered by chance and violence. Each has evidence, each has apps, and like most stories written in stone and silence, the truth may be a bit of both. But for now, let's sit quietly with the image of that early Earth, hot, raw and waiting. A planet still spinning itself into shape, not yet blue, not yet ready for life, but already holding, deep inside or somewhere in space, the seeds of a future rain. Picture the Earth as a deep-breathing organism, one whose lungs lie not in the sky but within molten rock. Long before there were oceans, before the sky could hold clouds or the surface could feel rain, there may have been water, but not in the form you know, not as lakes or rivers or dew on a leaf. This water, if it existed, was locked away, tucked inside crystals, embedded in minerals, hidden deep beneath the crust in the vast and restless mantle. It was there, perhaps from the beginning, waiting to be set free. This is the idea behind what scientists call the internal origin theory, that water didn't arrive from the stars, but was instead forged with the Earth itself. The building blocks that formed our planet, the rocky dust and planetary fragments that coalesced over millions of years, weren't entirely dry. Even inside the snowline, even so close to the sun's heat, some minerals can hold onto water in trace amounts, not in pools or droplets, but as part of their very structure. One such mineral is olivine, a greenish crystal found in abundance within the Earth's mantle. Olivine, along with minerals like pyroxene and ringwoodite, has the remarkable ability to incorporate hydrogen and oxygen atoms into its lattice under high pressure. This isn't water in any normal sense. It's not liquid, not flowing, but the ingredients are there, bound within the rock like letters inside a sealed envelope. Under the intense conditions deep underground, these elements are stabilised, waiting for the planet's movements to bring them closer to the surface. As the Earth cooled and began to differentiate, its iron sinking inward to form a dense core, its lighter elements rising to build a crust, the interior didn't rest, it churned. Mantle convection, driven by residual heat and radioactive decay, created slow rolling currents of rock. These currents gave rise to volcanism and plate tectonics, two of the most powerful forces Earth has ever known. Volcanoes are not merely fountains of lava, they are vents through which the planet releases its buried breath, and part of that breath is water. As molten rock from the mantle rises toward the surface, pressure decreases. This release of pressure allows the minerals to break down, and in doing so they release their locked-in volatiles, gases like carbon dioxide, sulfur dioxide, and crucially, water vapour. This vapour escapes through volcanic plumes, mingling with ash and heat, and billows into the sky. Over billions of years, this outgassing may have filled Earth's early atmosphere with steam, thickening the air, darkening the skies, and laying the groundwork for rain. It would not have been a quick process. The Earth's first crust was thin and unstable. It formed and reformed under bombardment and heat. But over time, as the surface cooled and hardened, as volcanoes erupted and oceans of lava solidified, the water vapour began to linger. The atmosphere, once too sparse to hold, heat or pressure began to trap both. And when temperatures finally dropped below the condensation point of steam, the first clouds may have formed, not the small, tidy clouds of today's afternoon skies, but thick, endless masses of storm-filled mist. And then came the rain that fell not for days or weeks, but perhaps for centuries, rain that pooled in ancient basins, carved channels into newly formed rock, softened landscapes that had never felt touch. In this view of Earth's history, the planet was not filled by a sudden arrival of alien ice, but by its own slow exhale. Its own volcanic whispering gave rise to lakes and seas, and while the atmosphere thickened and cooled, the surface began to darken and shimmer with water. This theory, though elegant, comes with limits. The amount of water we now find on Earth, over 1.3 billion cubic kilometres in oceans alone, raises a daunting question. Could volcanism and mineral-bound water really produce so much? Some geologists believe yes, especially when you account for the planet's massive mantle volume and the timescales involved. Others argue that internal processes likely contributed, but not completely. They suggest that while Earth may have exhaled much of its water, it likely needed help to fill its oceans. But the evidence for internal contribution is strong. Samples of mantle-derived rocks, such as those brought up in volcanic eruptions or from mid-ocean ridges, often contain small inclusions of water. Laboratory studies have shown that ringwoodite, a high-pressure form of olivine found deep in the mantle transition zone, can hold up to 1.5% of its weight in water. If even a fraction of the mantle contains such hydrated minerals, the total reservoir of hidden water could rival or even exceed the volume of water on Earth's surface. And that's not just academic curiosity. It means that water is still cycling, rising through volcanoes, sinking through subduction zones, being locked and released as the tectonic plates shift across the planet's skin. The Earth, in this sense, is not a finished system. It is still breathing, still sweating, still whispering vapour into the sky. So as you listen to the quiet drip of a faucet or watch mist curling through a morning field, remember this. Some of that water may have come not from a distant comet or frozen asteroid, but from the stone beneath your feet, brought upward by pressure and heat, released through fire, cooled by time, and finally caught by gravity in a quiet pool of rain. There's another possibility, one that doesn't begin within Earth at all. Instead, it begins out in the colder reaches of the early solar system, beyond the orbit of Mars, beyond even the asteroid belt, where temperatures drop low enough for water to freeze and remain stable. Out there, past what planetary scientists call the frost line, water was not rare or hidden. It was abundant, locked in ice, bound to dust, and carried inside countless fragments of rock and rubble drifting through the dark. These were the carbonaceous chondrites, icy comets, and ancient leftovers of planetary construction. And some of them, flung from the outer solar system by gravitational chaos, found their way inwards toward the newly forming Earth. This is the second major theory, that Earth's water came from space, not from vapour released slowly from the mantle, but from icy bodies that collided with the planet, delivering water like cosmic messengers carrying liquid in stone. It sounds improbable at first. After all, Earth is a closed system now, and space seems empty and still. But in its earliest days, the solar system was far from quiet. It was a violent, turbulent environment, with young planets shifting positions, gravitational forces tugging at loose debris, and billions of small bodies flying through space with unpredictable paths. During this time, known as the Late Heavy Bombardment, a chaotic period roughly 4 billion years ago, Earth and its neighbouring planets were bombarded by asteroids and comets at an extraordinary rate. Many of these projectiles came from the outer solar system, their trajectories altered by the giant planets, especially Jupiter, whose immense gravitational pull acted like a cosmic slingshot, flinging icy rocks into the inner regions. These incoming objects were not dry. They carried water locked within their mineral structures and frozen in their cores. The idea that these impacts could deliver water isn't just speculation. We know from meteorite studies that carbonaceous chondrites, a specific class of ancient water-rich asteroids, contain up to 20% water by weight. Not in the form of pools or ice sheets, but chemically bonded to their minerals. When these meteorites strike a planet, especially one with a molten or fractured surface, that water can be released, contributing to an atmosphere or pooling in surface basins once the crust cools. One of the key pieces of evidence for this theory comes from studying deuterium to hydrogen ratios, or DH ratios, in different sources of water. Deuterium is a heavier isotope of hydrogen, and the ratio between these two types of atoms acts like a chemical fingerprint. Earth's ocean water has a very specific DH ratio. Scientists have compared this ratio to that found in different potential sources, comets, asteroids, interstellar dust, and what they found is striking. Most comets, especially those from the distant Oort cloud, have DH ratios significantly different from Earth's, suggesting that while they contain water, it is not the same kind that fills our oceans. However, many carbonaceous chondrites match Earth's DH ratio very closely, pointing to them as the more likely source. These rocky asteroids were once considered unlikely water bearers, but now they appear to have played a central role in Earth's hydration. This perspective changes the story. It means that Earth's oceans may be the result of cosmic collisions, of randomness wrapped in inevitability. That water arrived not from within, but from beyond, flung here by chance, impact, and gravity. The Earth, too hot and dry on its own, needed help from the cold places, and that help came violently, through impacts that shook the planet, cracked its crust, and filled its skies with steam. But this story isn't just about destruction. With each impact, not only was water delivered, but energy was released, minerals were redistributed, and the surface evolved. Some of the water vaporized instantly, only to condense again as the atmosphere cooled. Some was absorbed into rock, some flowed into low-lying regions, and some remained in the air, waiting for the great rains to begin. There's still debate, of course. Some scientists argue that asteroidal delivery alone couldn't account for all of Earth's water, especially considering how much may have been lost to space in the planet's early atmosphere-less days. Others suggest that both internal and external sources likely contributed. Water released from deep minerals, combining with water delivered from space to create the reservoirs we see today. It's also possible that Jupiter itself played a dual role, both stirring up the asteroid belt and protecting Earth from larger threats. Its gravitational presence may have diverted some impactors away from Earth, sparing the planet from more catastrophic collisions, while still allowing smaller, water-rich asteroids to pass through. In this way, Jupiter becomes not just a sculptor of the early solar system, but a quiet guardian. Too far to touch, but close enough to influence everything. And as Earth cooled, as its crust thickened and atmosphere stabilised, the stage was set. Water, however it arrived, whether whispered from the mantle or hurled from the stars, began to gather, first in thin pools, then in deeper basins, until eventually it covered more than 2/3 of the surface, and with it came the potential for life. To look at the ocean now is to look at something ancient, foreign, and strangely familiar. It is Earth's memory of a time before life, a time of rock and dust and frozen messengers, and each wave, each droplet, is part of a gift sent across millions of miles, a gift wrapped in stone and flame and open not with hands, but with time. To understand the full story of Earth's water, we must now pause beneath a sky filled not with clouds but with fire. Imagine looking up 4 billion years ago and seeing not just stars but constant flashes, streaks of light, distant booms, and the endless arrival of stone and ice from the outer reaches of the solar system. This was the time of the late heavy bombardment, an era of astonishing violence, and strangely perhaps, of nourishment. The late heavy bombardment, or LHB, is believed to have occurred roughly 3.8 to 4.1 billion years ago, a relatively short time after Earth first formed. During this period, the inner planets, Mercury, Venus, Earth and Mars, were relentlessly pelted by asteroids and comets. These weren't rare stray objects. They came in waves, their origins disturbed by the shifting gravitational architecture of the young solar system. The evidence for this bombardment comes from many places, but perhaps most vividly from our own moon. Unlike Earth, which has withstood and tectonics to erase its scars, the moon preserves its wounds. Craters across its surface tell a story of impacts so frequent and so powerful that, had they struck today, the consequences would be catastrophic. But in the young Earth's case, these impacts may have been more than destructive. They may have been delivery systems, bringing not only energy and chaos, but also volatile compounds, including water. These were not gentle arrivals. Some of the asteroids that struck Earth during this time were dozens or even hundreds of kilometres across. The force of their impact would have melted rock, vaporised oceans if they already existed, and launched debris back into space. But in doing so, they also may have seeded Earth with vital ingredients: carbon, nitrogen, and most importantly, water. The question then is, what stirred this storm? Why did so many objects previously minding their own quiet orbits suddenly come crashing inward? The answer lies in part with the giant planets, especially Jupiter and Saturn. During the early days of the solar system, these massive bodies didn't form exactly where they sit today. Instead, models suggest that they migrated, moving slightly closer to the Sun before being pulled back out again. This movement, though subtle over astronomical scales, was enough to destabilise the orbits of countless small bodies, especially those in the outer asteroid belt and the icy Kuiper belt beyond Neptune. As Jupiter moved inward and outward, it acted like a gravitational blender, stirring the solar system's contents and sending waves of debris inward toward the terrestrial planets. Earth, with its growing gravity well and a molten surface, became both target and crucible, absorbing impacts, shaping its skin, and slowly collecting water from the fragments that struck it. One of the most significant impacts in this chaotic period may not have occurred during the LHB itself, but even earlier, the moon forming, collision. According to the prevailing theory, Earth collided with a Mars-sized body known as Theia in the very early stages of planetary formation. The impact was so violent that a massive portion of Earth's outer layer was ejected into space, where it eventually coalesced into our moon. This impact likely had several consequences relevant to water. First, it would have remelted much of the Earth's surface, resetting any early crust and potentially removing volatile elements through vaporization. But it may also have altered Earth's internal composition in a way that helped it retain volatiles afterward. The Earth that emerged from this collision was hotter, yes, but also more chemically complex, and possibly better suited to trapping and recycling water through its mantle and atmosphere. And the moon itself, though small and distant, played a subtle role in shaping Earth's future. Its gravitational influence stabilised Earth's axial tilt, which in turn stabilised the planet's seasons and long-term climate. Without the moon, Earth's tilt might have varied chaotically, swinging from upright to extreme angles, creating environmental upheaval that would make long-term water retention, and eventually life, much harder to sustain. In this sense, the moon is not just a silent observer in our skies, it is a quiet architect of habitability. The impacts continued. Some were enormous, scarring entire continents. Others were smaller, like soft raindrops on a hot surface. Over millions of years, these bombardments delivered not only water, but also the shock energy needed to fracture the crust, creating places for that water to gather, flow, and eventually cycle. Earth's surface became more porous, more dynamic, and more connected. As the bombardment waned, and as the planet slowly cooled, the pieces began to settle. An atmosphere thickened. Rain fell for the first time in earnest. And in the low places, between mountains pushed up by tectonic churn, in the basins formed by ancient impacts, water began to gather and stay. It's important to remember that while the LHB sounds cataclysmic, and in many ways it was, it also helped shape the conditions for life. It was both destroyer and deliverer. It brought fire, but it also brought the elements that fire could not create. Without this storm of falling rock and ice, Earth might have remained dry, or worse, unstable. With it came transformation, and eventually the oceans. So the next time you look at the moon glowing softly in a quiet night sky, consider the violence that brought it into being, and consider the silence that followed. The stillness after impact, the slow cooling, the first drop of rain falling on black rock unnoticed, and the billions that followed. The ocean, it turns out, may have been born in fire and fury, and then carried forward by gravity, chemistry, and the deep patience of time. And then, at last, the rains came. It's hard to say precisely when Earth's first true rain began to fall. The timeline is lost in billions of years of shifting crust and recycled rock, and there are no witnesses left to tell us what it felt like. But the evidence, scattered across ancient zircon crystals and isotope ratios, tells a quiet story. After the chaos, the planet cooled, slowly, gradually, persistently. And as it did, the skies began to change. For countless millennia, Earth's atmosphere had been thick with volcanic steam, carbon dioxide, ammonia, and other gases expelled from deep within. These early emissions, combined with the volatiles delivered by asteroids and icy bodies from beyond, formed a dense, heavy blanket around the still-forming crust. Temperatures remained high for a long time, too high for liquid water to persist on the surface. Any rainfall would have vaporized on contact with the hot rock, like a droplet hitting the coils of a stove. But over time the surface lost its molten glow. The crust thickened, cooled, and began to solidify into stable ground. Oceans didn't arrive in a moment of drama, but in a long, drawn-out act of condensation and quiet descent. As Earth cooled below the boiling point of water, the thick steam in the atmosphere began to condense into droplets. These droplets gathered into clouds unlike any we see today. They would have been enormous, dark and constant, spanning whole continents, dense with moisture, heavy with a kind of ancient inevitability. When they released their burden, it was not as drizzle or passing shower, but as a deluge that lasted far longer than a storm. It was as if the sky, after holding its breath for eons, exhaled in torrents. Rain fell, and fell, and fell. The surface, still warm and fractured, received the water like a sleeping body stirred from fever. At first, much of it evaporated again, pulled back into the thick air, but as the cooling continued, some water began to stay. It gathered in cracks, in craters left by ancient impacts, in basins formed by the shifting of plates beneath. Pools became ponds, ponds joined into lakes, lakes overflowed and became rivers, and slowly the first oceans began to form. These early oceans were not the clear blue expanses we imagine today. They were murky, filled with dissolved minerals, stirred constantly by volcanic activity, and likely shrouded under clouds for hundreds of thousands of years. The Earth was still an active, restless world, tectonic plates shifting, volcanoes spewing new rock, the crust pulling apart and crashing together. But now water had entered the equation. It began to shape the surface, not just through erosion but through participation. Water cooled lava, fractured rock, and transported sediment. It began the long process of sculpting coastlines and forming the landscapes that would one day hold forests, fields, and cities. At the same time, the oceans began to interact with the atmosphere. Water vapour rose and fell, carbon dioxide was absorbed and trapped. New chemical reactions began, altering both the composition of the air and the temperature of the planet. In this way, water didn't just arrive, it helped stabilise the very environment it was shaping. The same oceans that covered the Earth's surface also began to regulate its climate, softening extremes, spreading heat, and creating feedback loops that would eventually support life. And life, remarkably, didn't wait long. In the warm, mineral-rich waters of these early oceans, under the skies heavy with clouds and lightning, chemistry began to stir. Simple organic molecules, perhaps carried by meteorites or formed at hydrothermal vents along the ocean floor, began to link together. They formed chains, loops, membranes, and in time, no one knows quite how, some of them began to replicate. These were not yet cells, not truly alive by modern standards, but they were the seeds of something extraordinary, and water was their medium. It allowed molecules to meet, to react, to drift, to combine and reform. Without water, these early steps toward life would have been impossible. Some scientists believe that the very first life may have emerged near hydrothermal vents, places where seawater seeps into the crust, is superheated by magma, and rises again full of minerals and energy. These vents, surrounded even today by strange ecosystems of tube worms, clams, microbial mats, offer a glimpse into what Earth's earliest biological experiments might have looked like. Life, in this view, began not in sunlight but in shadow, not in calm pools, but in churning fissures deep beneath the sea. Wherever it started, life quickly became part of the water cycle itself. Microorganisms helped cycle nutrients, altered the chemistry of oceans, and eventually began producing oxygen through photosynthesis. The oceans, once merely containers of water, became cradles of complexity, alive with drifting bacteria, algae, and eventually larger forms of life. It would take billions of years for this microbial murmur to become something as familiar as a fish, or a tree, or a human. But the foundation was laid early, in waves stirred by wind and warmed by a sun unseen filtered through clouds. So when you look at the ocean today, whether from a rocky cliff, a quiet shore, or the window of a plane, you're looking at something ancient and sacred. Not because it is vast or deep, though it is both, but because it is the original. It holds memory, it holds heat. It holds in its shifting surface and quiet depths the story of how this world became alive. The arrival of Earth's water, whether from deep inside or far beyond, was never just about chemistry. It was about timing, patience, the strange harmony of elements meeting under the right conditions, and once water began to gather, it never left. it only moved, rained, evaporated, froze, melted, drifted and pooled. It became the rhythm of a planet, the pulse behind every cloud, the soft breath behind every breeze. The oceans are not ancient because they are old, they are ancient because they are continuous, because every drop carries the echo of rain that once fell on stone. If you were to stand on the surface of Mars today, you would see a landscape sculpted by silence. Red dust stretches to the horizon, interrupted by ancient craters, jagged cliffs, and the long, meandering traces of what once was. The air is thin and cold, so thin, in fact, that you'd need a pressure suit just to survive. And yet, carved into the surface, almost defying belief, are the unmistakable signs of flowing water. Deep channels wind their way through valleys. Sediment fans spread out at the mouths of craters. Layered deposits mark where lakes may have rested, shifting and shrinking over time. Mars, for all its aridity now, remembers the rain. These features were not made by wind or lava alone. They bear the unmistakable fingerprint of liquid water, of erosion, transport and deposition. Some of the channels are hundreds of kilometres long, with tributaries that mirror the branching patterns of river networks on Earth. They begin in highlands and descend into lower basins, following the pull of gravity. Others appear as abrupt outflow structures, formed by sudden and catastrophic releases of water. Floods so massive that they may have reshaped entire regions in days. And in places like Jezero Crater, now famous thanks to the Perseverance rover, you can see what appears to be a preserved delta, where sediment once spread into a fan shape as water slowed and deposited its load. For decades, these features puzzled scientists. Early observations, limited by low-resolution imagery, left room for debate. Could wind alone have carved these gullies? Were they volcanic in origin? But as technology improved, especially with orbiters like Mars Reconnaissance Orbiter and landers like Curiosity and Perseverance, the picture became clearer. The mineral composition of the soil, the layering of sediments, and the erosion patterns all point to the same quiet truth. Mars once had water, and not just frozen water hiding at the poles, but liquid water flowing across its surface. This realization changed everything. For much of the 20th century, Mars had been imagined as a dry, dead world, a dusty sibling to Earth, devoid of life or drama. But the new evidence suggested something far richer. If water once flowed on Mars, then the planet must once have had conditions that allowed it. Temperatures warm enough, an atmosphere thick enough, and a cycle, however brief, that could support rain, rivers, lakes, and possibly even shallow seas. We now believe that Mars experienced its wettest era during a period known as the Noachian Epoch, around 4.1 to 3.7 billion years ago. During this time, the surface was shaped by heavy bombardment, but also by climate conditions that allowed water to move and gather. Craters from this era often show signs of erosion. Some were clearly transformed into basins, filled and refilled with standing water. There may even have been rainfall, not as we know it perhaps, but enough to drive erosion and feed runoff into larger bodies. What kind of water system was this? Likely not a global ocean, though some hypotheses suggest that a northern basin may have once held a sea. But the more supported view is that Mars hosted a patchwork of regional lakes, river systems and possibly transient seas, connected perhaps by a primitive water cycle. The presence of hydrated minerals, such as clays and sulfates, confirms that water not only flowed but lingered, interacting chemically with the Martian crust. These minerals form only in the presence of liquid water and require it to be present for extended periods. Their existence means that Mars was not merely splashed by water but soaked, even if only temporarily. It's a strange thing standing on a dry world and seeing the bones of rivers. You can almost hear them if you try. Feel the pull of gravity as the water rushed along, sense the slow widening of valleys, the rippling of shallow lakes under a dusty pink sky. You can picture the sediments settling layer by layer in calm basins or stirred up in rushing floods. You can imagine clouds gathering in the cold air, perhaps releasing rain that ticked gently against the ground. and then, eventually, stopped. Mars holds these memories in stone, unlike Earth, where erosion, vegetation and tectonics constantly rewrite the landscape. Mars keeps its past close to the surface. A valley carved 3 billion years ago may still look almost exactly as it did when the water disappeared. The absence of water today does not erase its former presence. In fact, it preserves it. Each dried-up riverbed, each fossilized delta, each layered hill of clay-rich soil is a testimony, not just to what Mars lost, but to what it once had. In this way, Mars becomes more than a planet. It becomes a story, written in silence and time. A story of potential, of brief abundance, and of a great retreat. And unlike stories told on Earth, where memory fades and evidence crumbles, this one remains etched in stone, suspended beneath the dust, waiting for a reader with the right tools and enough patience to understand it. And we are beginning to understand, with each rover that lands, with each drill sample, each spectral reading, each dusty panorama sent back from across the void, the image becomes clearer. Not of a world that was always dead, but of one that lived, at least for a time, with water. And wherever there is water, there is the question of life. Perhaps it never took root, or perhaps it vanished with the rivers. But the fact that we can even ask the question at all means that it has, once, mattered in a very familiar way. If Mars once held rivers and lakes, if water truly shaped its surface and left behind those elegant valleys and scattered mineral clues, then an inevitable question follows, gentle but insistent. What happened? Why didn't the water stay? Why, unlike Earth, did Mars fail to hold on to its liquid treasure? To understand this, we must first consider Mars itself, not just the features we can see, but the traits we cannot. Mars is a smaller planet than Earth. It has roughly half the diameter and only about 1/10 the mass. That difference matters, not just for surface gravity, but for what lies beneath. A planet's ability to hold onto its atmosphere, to maintain internal heat, and to drive protective forces like magnetic fields is all influenced by size. In the quiet arithmetic of the cosmos, being small means losing more than just mass. It means losing time. When planets form, they inherit energy. Some of it comes from the collisions of accreting material, some from the decay of radioactive elements, and some from the very act of compression under their own gravity. This energy becomes heat. And in large planets like Earth, that heat is trapped for billions of years, powering geologic activity, tectonic movement, and a dynamo in the core that generates a magnetic field. Mars, however, cooled more quickly. Its core solidified earlier in its history, and when it did, something subtle but essential faded away. Without a spinning, molten core, Mars could no longer generate a strong magnetic field. And without that magnetic field, its atmosphere, already thin due to the planet's weaker gravity, was left exposed. The solar wind, a constant stream of charged particles from the sun, now had nothing to stop it. On Earth, our magnetic field bends these particles away, guiding them toward the poles where they create auroras but do little harm. Mars, unshielded, could not deflect the wind. The upper layers of its atmosphere were stripped away, slowly but persistently, like dust blown from a dry stone. This was not a sudden event. It took millions of years. But with each gust of solar radiation, Mars lost more of the gases it needed to keep its atmosphere dense, and as the pressure dropped, so did its ability to support liquid water on the surface. On Earth, atmospheric pressure keeps water in a delicate balance. It allows lakes to form, rain to fall, oceans to persist. But on Mars, that pressure began to fall below a critical threshold. The triple point of water, the minimum conditions under which water can exist as a liquid. Once the atmosphere thinned beyond that point, liquid water could no longer survive on the surface. It would either freeze instantly or sublimate directly into vapour. Rivers dried, lakes disappeared. The air itself could no longer hold the promise of rain. It's difficult to overstate the importance of a magnetic field in planetary evolution. Without it, a planet's atmosphere becomes a fragile veil, easily torn. But MAVEN's spacecraft, short for Mars Atmosphere and Volatile Evolution, has confirmed this. Orbiting Mars since 2014, MAVEN has measured how solar wind interacts with the planet's upper atmosphere. Its data shows that Mars is still losing particles to space today, albeit more slowly than in the past. It is a slow erosion, a quiet unravelling that began billions of years ago and has never entirely stopped. And yet Mars's surface still tells the story of a wetter past. This suggests that the planet's magnetic field and atmosphere must have held out for a time, long enough for water to flow, sediments to settle, and minerals to react with water. But the clock was always ticking, the planet was always cooling, the field was always fading, and once the protection was gone, the environment changed irreversibly. Mars's small size worked against it in another way too. A smaller planet means less gravity, and less gravity means that even a thick atmosphere struggles to stay in place. Molecules at the upper edge of the atmosphere can reach escape velocity more easily. They drift away into space, never to return. On Earth, gravity tugs these particles back. On Mars, gravity watches them go. This double vulnerability, cooling from within and stripping from without, meant that even though Mars began with potential, it could not sustain it. The ingredients were there, but the recipe did not hold. Some have wondered whether life could have emerged before this collapse. If Mars had warm, wet periods early enough, there may have been time for microbial life to form, perhaps near hydrothermal vents or underground aquifers, much like the earliest life on Earth. But if it did, that life would have faced an increasingly hostile environment. As the air thinned and the water vanished, survival would have meant going deeper underground, adapting to radiation, and enduring long winters without end. We have no evidence yet of such life, only the possibility. But what we do have is a portrait of a planet that lost what it once had, not from a single disaster, but from a series of slow, interconnected changes. It didn't fail, it simply changed course. The riverbeds dried not because they were flawed, but because the sky above them faded. Mars couldn't hold on, not to its warmth, not to its air, not to its water. And so it became the planet we see today, quiet, rust-red and cold, but not empty of meaning. For in its silence, Mars reminds us of how delicate planetary systems are, how much they depend on size, distance and deep time, how close Earth may have come to sharing the same fate. There's a moment in every story when the balance tips, not in a single loud crash, but in a subtle shift, an accumulation of small changes that quietly push the system past a point of return. For Mars, that moment came not in a great cataclysm, but in a long and quiet transition. A gradual unravelling of its atmosphere, a cooling of its surface, and a slow dimming of a world that once held rivers and storms. What began as a place of potential, if not warmth, then at least possibility, became over millions of years a planet encased in stillness. As the magnetic field faded and the atmosphere thinned, the very mechanics of climate on Mars began to collapse. To understand how this happened, it helps to return to one key concept: pressure. The atmosphere of a planet acts like a blanket, holding in heat and allowing water to exist in its liquid form. But it also acts like a container. If the pressure is too low, water can't stay liquid, no matter the temperature. Instead, it either freezes or jumps straight to vapour in a process called sublimation. On Mars, atmospheric pressure dropped below the triple point of water, the delicate balance where all three phases, solid, liquid and gas, can coexist. Below that point, liquid water is not soluble. It can't form coast puddles or lakes. It can't flow even if the temperature rises. The loss of pressure alone was enough to turn Mars into a dry world. But the transformation didn't stop there. As the atmosphere became thinner, so too did its ability to trap heat. Even if early Mars was never as warm as Earth, it likely had a thicker carbon dioxide-rich atmosphere that created a greenhouse effect, strong enough to allow for some warming. Once that CO2 began to dissipate, or worse, to freeze out as temperatures dropped, the climate entered a dangerous feedback loop. Cold air holds less water vapour. Water vapour, a powerful greenhouse gas, became even scarcer. The remaining carbon dioxide, bourse, no longer sustained by a dynamic system of outgassing and circulation, began to condense at the poles, forming ice caps not just of water, but of dry ice, solid carbon dioxide. This process is known as atmospheric collapse, and while it sounds dramatic, it happened slowly. One season led to another, each a little colder than the last. Over time, the Martian atmosphere became so thin and cold that large-scale weather ceased. No more flowing clouds, no more storms of liquid precipitation, only dust devils and the occasional thin, icy fog. Temperatures plunged. The average surface temperature of Mars today hovers around 63 degrees, with some nights in the polar regions dipping well below 100 degrees. Water, if exposed to these conditions, would freeze solid or vanish into vapour in seconds. The evidence for this transformation is not just theoretical. Instruments on board orbiters and rovers have detected glacial features in Martian terrain, striations, moraines, and remnants of slowly moving ice sheets. These suggest that even as Mars dried, it continued to store water in solid form, preserving it in the subsurface and at the poles. But the days of flowing water were over. The cycle was broken. Rain no longer fell, and rivers no longer ran. And what replaced it? Silence mostly. A silence interrupted only by wind, by sandstorms that whip across the plains and climb the rims of long-dead craters. Mars became a planet defined not by what it had, but by what it lost. The colour red, so familiar in our images, is not just the result of iron-rich dust, but a sign of oxidation, of chemical reactions that once needed water to begin, and then were left frozen in place. Perhaps the most poignant part of this collapse is that it was not total. Water remains. Ice clings to the poles and hides in shadowed soils. Traces of vapour swirl in the upper atmosphere. The climate did not fail completely. It simply fell into stasis. The engine stopped turning. The cycle slowed to a crawl. This deep freeze makes Mars feel distant, but it is, in a strange way, intimately connected to Earth. The two planets likely shared similar starting conditions. They both formed from the same dust, orbited the same sun, and show evidence of early volcanic and meteorologic activity. And yet their fates diverged. Mars, too small and too quick to cool, became a frozen storybook. Earth, larger and more fortunate, retained its heat, its field, and its water. This divergence wasn't a judgment. It wasn't destiny. It was the delicate consequence of scale, of timing, and of the chaotic beauty of planetary formation. Mars teaches us that habitability is not a guarantee. It is a balance, a temporary gift. The climate we know here, the rain we rely on, the air that holds our breath in place, none of it is permanent. It is stable only because 1,000 invisible mechanisms continue to function beneath our feet and above our heads. And so when we study Mars, we are not just reading its history. We are measuring our own fragility, because if a world that once had rivers can end in silence, then our own rivers, though deep and ancient, deserve our attention. Not fear but awareness, not dread but reverence. The collapse of climate on Mars didn't come from war or industry. It came from nature, from a quiet unfolding of internal processes, from the fading of a core, from the loss of a field no one was there to witness. And if it happened there, it reminds us that planetary stability is not to be taken for granted. Mars still circles the sun, still watches Earth from a cold, dry distance, still holds, in its ice and dust, the memory of warmth. And perhaps, someday, we'll walk its dried riverbeds, not in search of what might be, but in humble reflection of what once was. For a world that lost so much, Mars still holds secrets. Though the days of flowing rivers are long gone, and the sky no longer carries clouds thick with moisture, water has not vanished entirely. It lingers, quietly, stubbornly, beneath the surface and at the poles, preserved in forms both familiar and strange. If the story of Mars once read like a slow retreat, the present is more like a pause, a moment caught in suspension. Not truly empty, not yet closed. The most visible reminders of water on Mars today are its polar ice caps, brilliant against the rust-red dust that surrounds them. These caps, located at the planet's north and south poles, grow and shrink with the seasons, expanding in winter and retreating in summer, much like their counterparts on Earth. But the similarity is superficial. On Earth, polar ice is made almost entirely of frozen water. On Mars, it's more complicated. The caps are composed of layered materials, water ice and dry ice, the latter being frozen carbon dioxide. During the frigid Martian winter, CO2 from the atmosphere condenses directly onto the surface, forming a layer of dry ice up to a metre thick. When spring returns, sunlight warms the surface, causing the dry ice to sublimate back into gas, leaving behind water ice as a more permanent fixture. Beneath these shifting layers, more persistent stores of water ice remain. Radar instruments aboard orbiters like the European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter have revealed extensive ice sheets buried just beneath the surface, even outside the polar regions. In some mid-latitude areas, this ice lies less than a metre below the dusty topsoil, close enough that future explorers might access it with modest digging. These findings suggest that while Mars appears dry, it still holds an enormous reservoir of frozen water. If melted, it could cover the entire planet in an ocean over 100 metres deep. But not all of Mars's remaining water is frozen. Trace amounts of water vapour exist in the thin atmosphere, although they are fleeting and vary with the seasons. Instruments on orbiters and landers have detected subtle shifts in humidity, frost forming on rocks overnight, and the brief appearance of fog-like mists in valleys and low-lying areas. These are not the kinds of phenomena that support life or agriculture, but they whisper of processes still at work, of water still cycling, however slowly, through the Martian air. One of the more intriguing discoveries in recent years came from radar scans beneath the southern polar ice cap. Scientists detected an area of unusually high reflectivity, a signal that, on Earth, would typically indicate the presence of liquid water. This sparked excitement and speculation. Could there be briny lakes buried beneath the ice? Could salts in the Martian crust lower the freezing point enough for water to remain liquid, insulated beneath layers of ice and dust? The idea is not far-fetched. Mars is known to contain perchlorate salts, substances that dramatically reduce the freezing point of water. In lab conditions, these salts can keep water liquid at temperatures far below zero, and if these salts are present in underground reservoirs, mixed with geothermal warmth from the planet's interior, it's plausible that briny pockets of liquid water still exist, locked away from the surface, sheltered from the hostile cold above. Whether such briny lakes truly exist remains an open question. Some scientists argue that the radar signal could have other explanations: unusual clays, tightly packed ice, or even layering effects that mimic liquid reflectivity. But the possibility is enough to fuel continued exploration. Because even if these lakes are real, they raise further questions. Could microbial life persist there, hidden from view? Could extremophiles, organisms adapted to harsh, salty conditions, survive in the dark, insulated depths of a frozen desert? So far, no direct evidence of life has been found on Mars, past or present. But its remaining water, however sparse, keeps the question alive. It keeps the search going. The Perseverance rover, currently exploring Jezero Crater, a site once home to a lake and river delta, is collecting samples and searching for biosignatures. These samples will eventually be returned to Earth, where they can be studied in greater detail than any robot could manage alone. And beyond the robots, there is us. If humans eventually walk on Mars, if boots touch down on its dust and hands reach into its frozen soil, Water will be a key resource, not just for hydration, but for life support, fuel production, and agriculture. We will need to melt it, purify it, and use it with care. In that way, the search for Martian water is not just scientific, it is preparatory. It is part of our tentative, thoughtful step beyond Earth. For now, Mars remains quiet, but not lifeless. Not in the strictest sense. It is filled with potential energy, frozen, buried, thinly suspended in vapour. It holds, even in its silence, the last echo of rivers and rain. It keeps those memories intact, not erased, but paused. The red planet still turns. The ice still grows and retreats. The vapour still drifts in the morning sun. And beneath the dust, perhaps, something still flows. Not loudly, not visibly, but patiently, waiting. In the quiet landscape of Mars, beneath its windswept dunes and within its frozen soil, lies a profound lesson. Not only about the history of a neighbouring planet, but about the delicate systems that make our own world possible. Mars, in its silence, becomes a kind of mirror, a reflection of paths not taken, or perhaps taken and then lost. And the more we study it, the more we begin to see that its story is not simply one of barrenness or failure, but of transformation, and of possibility balanced on a knife's edge. What Mars teaches us, more than anything, is how fragile habitability can be. For a time, it seems Mars was not so different from Earth. It had an atmosphere thick enough to support rain and lakes. It had active volcanoes, chemical reactions involving liquid water, and energy sources that could have powered the chemistry of life. It was not a frozen desert, but a dynamic living world. And yet, for reasons rooted in physics, geology, and cosmic timing, it could not sustain that state. The planet's small size meant it lost heat quickly. That led to the shutdown of its core dynamo and, in turn, the disappearance of its protective magnetic field. Without that shield, solar wind stripped the atmosphere away, thinning it until water could no longer exist as a liquid on the surface. Temperatures plummeted, carbon dioxide began to freeze out, and the climate collapsed into a long, cold stillness. None of these changes were dramatic when taken alone, but together they pushed the planet past a point of no return. Earth, by contrast, managed to hold on to what Mars could not. Our planet is larger, which helped it retain internal heat. That heat drives plate tectonics and a magnetic field that still protects our atmosphere from the solar wind. We sit in a habitable zone around the sun, where temperatures allow water to remain in all three states: solid, liquid, and gas. And perhaps most critically, we have an atmosphere thick enough and dynamic enough to maintain a stable water cycle over billions of years. But what if one variable had shifted? What if Earth had been just a little smaller, a little farther from the sun? What if our early impacts had stripped more of our atmosphere? Would we too now be dry, our rivers frozen in stone? The boundary between a living planet and a dead one is thinner than we might imagine. In this way, Mars becomes not just an object of study, but a cautionary presence. It reminds us that planetary systems are not fixed or guaranteed. They are ecosystems of rock, gas, heat and time, each interdependent and vulnerable to disruption. The magnetic field, the greenhouse gases, the tectonic churn beneath our feet, these are not background conditions. They are lifelines. And yet, despite its desolation, Mars also offers hope. The fact that it once held water, and perhaps still holds it beneath the surface, expands our understanding of where life might emerge. If a planet as seemingly inhospitable as Mars once had lakes and rivers, then so might many other worlds, planets orbiting distant stars, icy moons warmed by tidal forces, rogue planets holding subsurface oceans heated from within. Mars tells us that the ingredients for life are not rare. They appear again and again, shaped by the same physics and chemistry that govern our own world. In that sense, Mars is both a lost opportunity and a cosmic preview. It shows us what was possible and what might still be possible elsewhere. Its dry valleys speak not only of retreat, but of the universal processes that unfold across the galaxy. And if life never took hold there, or if it did and later vanished, Mars may yet help us understand why life persists here, and how to protect it. It's easy sometimes to take Earth for granted, to see the blue skies, the moving clouds, the endless dance of evaporation and rain, and forget how rare such systems are. Mars, with its thin air and rusted soil, invites us to remember, to appreciate that our oceans are not permanent fixtures, but dynamic features held in place by 1,000 quiet balances of temperature, of pressure, of magnetic shielding and geological movement. There is also a kind of beauty in Mars's resilience. Even in its frozen state, it continues to change. The poles breathe in and out with the seasons. Dust devils trace spirals across ancient plains. Subsurface water waits, perhaps only centimetres below the surface in some places, preserved like a memory. It is a world that did not die, but shifted into a different rhythm. A quieter, slower pulse, but not silence. In studying Mars, we are not just peering into the past, but looking into possible futures. It is a testing ground for ideas about climate, geology, planetary protection, and even the ethics of exploration. What does it mean to visit a planet that may once have been alive? What responsibilities do we carry when we land rovers, when we plan for human footprints? Mars, the red planet, holds no answers. But it does offer questions, and sometimes the questions are enough. They open our eyes to the wonder of our own home. They remind us that we are lucky beyond measure to live on a planet where water still falls from the sky. So tonight, as you drink a glass of water or listen to rain tapping gently at the window, remember that it could have been otherwise. Earth could have been dry. It could have shared Mars's fate, but it didn't. Not yet. And that's the quiet miracle we live inside every single day. Sometimes the difference between success and silence rests in things we cannot see. A planet's fortune isn't only in its oceans or mountains or cloud or birds. It begins much deeper, in its very bones. It begins with mass, with the weight of rock and metal pressed inward by gravity, and the silent heat that builds and churns inside a planet's core. In this quiet, molten heart, the future is written, not in grand sweeping lines, but in temperature gradients and the slow spinning of liquid iron. Earth and Mars began their lives in roughly the same neighbourhood of the solar system, both rocky, both born from swirling dust and gas, both shaped by collisions and cooled by time. But from the moment of formation, a fundamental difference existed. Earth was larger, by a wide margin. It had more mass, which meant more gravity, more heat trapped from formation, and more radioactive elements to keep that heat going. This inner heat is not just an interesting detail. It is the engine behind many of Earth's defining traits: tectonic movement, volcanic activity, and perhaps most importantly, a magnetic field. Deep inside the Earth, a layer of molten iron flows and rotates. This movement creates electric currents, which in turn generate a magnetic field, a vast invisible bubble that extends far beyond the surface, known as the magnetosphere. This field shields the planet from solar wind, that continuous stream of charged particles blowing out from the sun. Without this shield, those particles would slam directly into the atmosphere, eroding it molecule by molecule. But Earth's magnetosphere deflects them, guiding them harmlessly around the planet, or directing them toward the poles where they shimmer as auroras. It is one of the quietest, most essential forces in the preservation of Earth's water and air. Mars, on the other hand, never had this long-term protection. It's not that it never had a magnetic field, it did briefly. Evidence in ancient Martian rock shows magnetization. Lines frozen in minerals that suggest a once-active dynamo spinning like Earth's. But Mars, being smaller, cooled faster. Its core solidified relatively early in its history, and when it did, the dynamo shut down. The movement stopped, the shield dropped, and without it, Mars became vulnerable. With no magnetic field, Mars' thin atmosphere faced the full force of solar wind. Over time, this stream of particles stripped away gases, slowly peeling back the atmosphere layer by layer. The process was gradual but persistent. Molecules that help trap heat, protect water and support a hydrologic cycle simply drifted into space. Without enough atmospheric pressure, water could no longer remain liquid on the surface. It either froze or evaporated. Rivers dried up, clouds disappeared, the sky thinned to a dusty haze. Earth, by contrast, retained its internal heat far longer. Its dynamo persisted and continues to spin to this day. As a result, our atmosphere remains thick enough to support oceans, clouds, and a stable climate. It's easy to overlook something we cannot see, but Earth's magnetic field is as vital to life as oxygen or sunlight. Without it, we might be looking at a very different planet. There is another difference, one tied not just to size but to location. Earth orbits the Sun at an average distance of about 50 million kilometres. This puts it in the so-called Goldilocks zone, where temperatures are neither too hot nor too cold for liquid water to exist. Mars, by contrast, sits farther out, around 28 million kilometres from the Sun. This greater distance means it receives less solar energy. Even with a thicker atmosphere in its past, Mars would have struggled to maintain warmth. Once the greenhouse gases began to disappear, the planet had little chance of recovering. But Earth's distance is not a guarantee of warmth either. The early Sun was fainter, perhaps only 70% as luminous as it is today. This creates a paradox known in planetary science as the faint young sun. Paradox: Earth should have been frozen early on, yet somehow it stayed warm enough for liquid water to exist. The answer likely lies in our atmosphere, rich in carbon dioxide, methane and other greenhouse gases that trapped heat and stabilised the climate. Again, Earth's internal heat and geologic activity played a role. Volcanoes released gases into the sky, tectonics recycled carbon through rock and air, and the magnetic field ensured that these gases were not all swept away. Mars, smaller and colder, could not do the same. Its early warmth was fragile, dependent on a thick atmosphere it couldn't protect. Once the internal heat faded and the magnetosphere collapsed, the slow erosion began. No mechanism remained to replenish what was lost. The cycle broke, and with it the conditions for water and life. So when we compare Earth and Mars, we are not just looking at two planets, we are comparing two paths. One that led to oceans and forests, thunderstorms and coral reefs, cities and songbirds, and another that led to silence, stone and the soft breath of dust in a thin, dry wind. The difference was not magic, it was mass, distance, and the quiet spin of molten metal in the dark. It's humbling, really, to realise that so much of what we depend on comes from forces deep underground, from movements that we cannot hear or feel. The air we breathe, the rain that falls, the oceans that shimmer, all of it, in some way, is connected to the strength and longevity of a field we never see. Earth kept its heart beating long enough to build a sky that could hold water. Mars, in a sense, ran out of time, and yet, even in its stillness, Mars has not ceased to teach. By revealing what happens when these protective systems fade, it sharpens our appreciation for Earth's endurance. It shows us how fragile water can be, how easily it can disappear, and how much depends, not just on where a planet sits in space, but how long it can hold on to its inner warmth. If you've ever heard the tale of Goldilocks and the Three Bears, you'll remember that the little girl didn't settle for porridge that was too hot or too cold. She wanted something just right. In planetary science, we've borrowed that simple image to describe something profound, the habitable zone, a range of distances from a star where a planet might be neither scorched by heat nor locked in ice. Earth, as it turns out, sits comfortably in this cosmic middle ground, not too close to the sun, not too far, just right. Mars, by contrast, hovers near the outer edge of this zone. It's not so distant that it was always frozen, but it never quite had the warmth needed for long-term surface water to persist. Its position left it vulnerable to slight shifts in climate, atmospheric pressure, and solar output. It was a precarious place to try to hold on to oceans, but even Earth, sitting closer to the sun and cushioned by a thicker atmosphere, faced its own early climate mysteries, ones that required more than distance to resolve. One of the most fascinating puzzles in Earth's ancient past is known as the faint young sun paradox. According to models of stellar evolution, our sun was about 30% dimmer during Earth's early years than it is today. That level of solar radiation should not have been enough to keep the planet's surface warm enough for liquid water, and yet geological records show clear evidence of rivers, oceans, and even early microbial life going back more than 3.5 billion years. So the question lingers in the background of Earth's climate story. How did a young, faint sun manage to warm an entire planet? The most widely accepted answer is that Earth's early atmosphere was filled with potent greenhouse gases, carbon dioxide, methane, water vapour, released by intense volcanic activity. These gases trap heat, absorbing infrared radiation and keeping the planet's surface from freezing. But the balance had to be delicate. Too much carbon dioxide and Earth would have turned into a furnace. Too little and it would have been buried under a global ice sheet. That balance was maintained not by chance but by Earth's dynamic systems, its geology, chemistry and perhaps even its biosphere. The carbonate-silicate cycle, for instance, acts like a planetary thermostat. When Earth warms, weathering of silicate rocks increases, drawing carbon dioxide from the atmosphere and cooling the planet. When Earth cools, weathering slows, allowing CO2 to build up again through volcanic outgassing. This negative feedback loop helped regulate climate over geologic timescales. It's one of many ways Earth self-adjusts. A quiet, deep time dance that keeps the porridge warm but not boiling. Mars lacked this flexibility. With less volcanic activity and no active plate tectonics, it couldn't refresh its atmosphere. It couldn't recycle gases or stabilise feedbacks. And without a magnetic field, the gases it did release were slowly lost to space. Over time, Mars' climate system stalled. Whatever warmth it once held slipped away. But even Earth, with all its advantages, was not immune to extremes. Throughout its history, it has experienced several dramatic climate shifts, including episodes known as snowball Earths, periods where the planet may have been nearly or entirely covered in ice from pole to equator. These were not short ice ages. Some may have lasted millions of years. The trigger for such global freezes isn't fully understood, but it may have involved tectonic rearrangements, changes in solar radiation, or massive volcanic events. During these times, Earth teetered at the edge of habitability, only to pull itself back through greenhouse gas buildup from ongoing volcanic activity. Other periods were just as dramatic in the opposite direction. The Paleocene-Eocene thermal maximum, for instance, saw global temperatures spike due to massive carbon releases, possibly from methane hydrates melting or volcanic eruptions. Temperatures soared, oceans acidified, and ecosystems struggled to adapt. Yet through it all, the planet retained its capacity to rebound. The cycles, though extreme, never fully broke. This capacity for recovery, for climate resilience, is part of what sets Earth apart. Its size, internal heat, geological activity and biosphere all contribute to maintaining a habitable range. It doesn't mean Earth is perfectly stable, but it means Earth has mechanisms, slow, subtle, powerful, that gently push it back toward equilibrium after disturbance. Mars, with fewer tools at its disposal, had no such fallback. Its thin mantle, cooled core, lack of tectonics, and low gravity left it with no reliable thermostat. Once the sun dimmed or the atmosphere waned, Mars couldn't correct course. And without that resilience, temporary climate shifts became permanent ones. Warm periods passed into cold ones, and the cold never lifted. What this comparison reveals is that habitability isn't just about location. It's about the internal and external systems that can sustain stability across eons. Earth lives in a Goldilocks zone, yes, but it also works very hard in slow and hidden ways to stay there. It has survived faint suns and deep freezes, carbon spikes and volcanic winters, and still it holds oceans, forests and breath. And that teaches us something important. A planet can be lucky in its position, but it must also be lucky in its construction. It must be active, it must recycle, it must balance. And even then, there are no guarantees. So when you step outside and feel the breeze, or watch the sun set through drifting clouds, remember that this climate, this livable warmth, is not merely a product of distance. It is the result of invisible feedback loops, spinning iron deep underground, and a sky that has endured fire and frost and come back from the brink more than once. Earth may be just right, but only because so many things continue to make it so. In the middle chapters of planetary history, the story often turns not on what a planet is made of or where it stands, but on what it encounters. The characters shift from rock and gas to gravity and motion, and the narrative stretches across orbits and eons. One of the most influential yet unseen players in Earth and Mars water stories is Jupiter, that great banded giant far out beyond the asteroid belt. Though distant, its mass and motion have shaped the destinies of worlds, like a quiet conductor influencing the music without ever playing a note. Jupiter is the largest planet in our solar system, a behemoth of hydrogen and helium, more than 300 times the mass of Earth. Its gravity is immense, powerful enough to deflect comets, redirect asteroids, and sculpt entire regions of space. When it formed, Jupiter's presence disrupted the calm spiral of dust and rock around the young sun. It carved gaps into the protoplanetary disk, stirred up debris, and influenced the trajectories of countless smaller bodies. That gravitational mischief would prove to be both a threat and a gift. Much of what we believe about Earth's early water delivery comes down to icy bodies, comets, asteroids, and planetesimals rich in volatiles, being flung inward from the colder outer reaches of the solar system. These bodies, born beyond the snowline, carried water locked in stone and ice. But they didn't drift inward on their own. Many were nudged, redirected, or hurled sunward by the shifting influence of Jupiter's gravity. It didn't do this intentionally, of course, no planet thinks or chooses, but the effects were nonetheless profound. As Jupiter migrated slightly during the early solar system's evolution, it may have acted like a cosmic slingshot, disturbing the orbits of water-rich asteroids and sending them tumbling toward the inner planets. Earth, sitting in the path of this redirected material, received a share of the chaos, and with it, a generous delivery of water. These impacts were violent, reshaping the surface and stirring the atmosphere. But they were also transformative. They added to the reservoir of volatiles already present from Earth's own outgassing, tilting the balance toward oceans. Mars, however, sat in a more precarious position. Orbiting just beyond Earth and just inside the asteroid belt, it may have been caught in a gravitational no man's land. Too close to Jupiter's disruptive influence to enjoy the full benefit of water-rich deliveries, yet too far from the Sun to maintain the warmth and pressure needed to hold on to what it did receive. It was close enough to the action to suffer, but not close enough to thrive. The asteroid belt itself, located between Mars and Jupiter, tells part of this tale. Instead of forming into a planet, the belt became a scattered collection of rocky remnants. Jupiter's gravitational tugs prevented these bodies from coalescing. Instead, they remained in dynamic motion, crashing, fragmenting, and occasionally being thrown inward toward the terrestrial planets. Mars, located at the inner edge of this maelstrom, was more exposed to large impacts. Its surface still bears the marks. Massive craters like Hellas and Argaea, signs of impacts that may have altered its climate or even stripped away parts of its atmosphere. Meanwhile, Earth, slightly closer to the Sun, slightly more massive, stood just far enough away to avoid the worst of the bombardment, while still capturing enough icy projectiles to seed its oceans. This positioning wasn't perfect safety, of course. Earth too was bombarded, especially during the late heavy bombardment, but its larger size and protective magnetic field gave it better odds of recovery. It absorbed the shocks, retained its atmosphere, and eventually cooled into a planet of rivers and rain. Jupiter's role didn't end with these early deliveries. Even today, it continues to influence the inner solar system. Its gravity deflects comets that might otherwise strike Earth, acting as both shield and occasional hazard. In this way, it continues to shape the risk landscape for our planet. It has been called both protector and destabilizer, a planet that helped give Earth its oceans while also sending objects our way that could one day do harm. This dynamic role makes Jupiter a kind of paradox, essential and unpredictable, beneficial and dangerous. But in the story of water, its influence is hard to overstate. Without its early interference, the inner planets might have remained too dry to ever host life. With too much interference, they might have been scoured clean by impacts. Earth's position, near enough to receive, far enough to survive, was a stroke of luck on a cosmic scale. And Mars sat just beyond that sweet spot. Its smaller size made it less able to absorb the impacts it received. Its atmosphere was thinner, its crust less dynamic. When hit, it couldn't bounce back the way Earth could. Its vulnerabilities were not just physical but positional. It was caught between a generous giver and an indifferent star, and in that narrow space it could not quite hold on to its hope. Still, Mars teaches us about the architecture of planetary systems. It shows us that the fate of a world is never shaped by one factor alone. It is a web of relationships, with the Sun, with neighbouring planets, with the leftover debris of formation. And it reminds us that Earth's watery fortune is not just a result of chemistry or heat, but of orbit and gravity, of quiet nudges and long-forgotten collisions. In the great clockwork of the solar system, Earth ended up in a place where it could be transformed by falling ice. Mars, just a little further out, received a different script, drier, harder, colder, not by much, just enough. As we near the end of this quiet comparison between two planets, one blue, one red, it becomes increasingly clear that Earth's ability to hold water, and with it, life, cannot be traced to a single cause. Instead, it is the product of interlocking systems, of unlikely alignments, and of events that could so easily have turned out differently. Some of these forces were internal, tectonic, magnetic, atmospheric. Others were external, gravitational nudges, distant collisions, a shifting solar output. And still others were born of sheer timing, of where Earth happened to be when the pieces of a much larger cosmic puzzle began to fall into place. Perhaps the most significant of these coincidences was an impact, not just any impact, but the giant collision that formed the Moon. According to the prevailing theory, a Mars-sized object, sometimes named Theia, struck the young Earth in a glancing blow, not quite direct, but not quite passing by either. The energy of the collision was enormous, melting the outer layers of both bodies, launching debris into orbit and changing Earth forever. Much of that debris eventually coalesced into our Moon. This was not just an act of destruction, it was an act of transformation. The Moon's presence has shaped Earth's destiny in subtle but profound ways. Most importantly, it stabilised Earth's axial tilt. Without this stabilising effect, Earth's tilt might have varied wildly over time, swinging from near upright to extreme angles. Such variations could have triggered massive climate shifts, ice ages and tropical heat swapping places unpredictably. But thanks to the Moon, Earth's tilt has remained within a relatively narrow range for billions of years, ensuring seasonal consistency and long-term climate stability. Mars, with no large moon of its own, lacked that stabilising influence. Its tilt has varied significantly, swinging across tens of degrees over geological timescales. These chaotic shifts likely contributed to the planet's inability to maintain a consistent climate. Water, already threatened by the thin air and cold temperatures, was further compromised by a wobbling axis that disrupted any hope for regular seasons or a stable water cycle. Another crucial factor in Earth's stability is plate tectonics. Beneath our feet, the crust is broken into massive slabs that move slowly but persistently, driven by heat from the mantle. This movement recycles materials between the surface and the deep Earth, shaping continents, building mountains, and, most critically, regulating the carbon cycle. Volcanic eruptions release carbon dioxide into the atmosphere, while weathering and sedimentation trap it back into rock. Subduction carries those rocks deep into the mantle where the cycle begins again. This carbon silicate loop acts as a planetary thermostat, adjusting greenhouse gas levels to keep the climate within habitable bounds. Mars, once again, falls short in this regard. With a thinner crust and a smaller, cooler mantle, it shows no evidence of ongoing plate tectonics. It has volcanoes, some of the largest in the solar system, but they are ancient and quiet. Without plate motion, Mars cannot recycle its surface or regulate its atmosphere. What it gains, it keeps. What it loses, it cannot replace. Then there is water itself, not just as a substance but as a participant in planetary life. On Earth, water is not static. It flows, it evaporates, it freezes and melts. It moves through air, land and ocean in a process so steady and ancient that we almost forget to marvel at it. The hydrologic cycle, powered by sunlight, maintained by gravity, and guided by planetary rotation, is what makes weather possible, what carves valleys, fills aquifers, and nurtures ecosystems. But the cycle depends on more than just water. It needs a thick atmosphere to hold vapour, enough surface warmth to prevent freezing, and a magnetic field to keep the air in place. It needs continents and basins, clouds and winds, seasons and storms. Earth has all of these. Mars has fragments, a whiff of vapour, a pocket of brine, a swirl of dust. But the cycle no longer spins. All of these differences, the moon's influence, plate tectonics, the hydrologic cycle, are not isolated traits. They are interdependent systems, each reinforcing the other. The moon helps stabilise the axis, which helps preserve seasons, which influence rainfall, which affects erosion, which contributes to the carbon cycle, which in turn influences global temperature and ocean chemistry. It is a web, not a ladder. And Earth, somehow, manages to hold all the threads. Could another world be so lucky? Perhaps. But even among the growing list of exoplanets we've discovered, none so far display the same delicate orchestration. They may have oceans, but no plate tectonics. They may have moons, but no breathable air. They may orbit the right distance from their stars, but with atmospheres that choke or skies that bake. The chances are not zero, but they are narrow, shaped by a long chain of coin flip moments. Earth has weathered asteroid strikes, mass extinctions, ice ages, and thermal spikes. It has shivered under snowball conditions and sweltered through volcanic eras, and yet through it all the cycles continued. Water flowed, the atmosphere rebounded. Life, once sparked, did not fade. It adapted, it branched, it sang. This is not to say that Earth is invincible. Its balance is maintained by forces we are only beginning to fully understand. The magnetic field could falter, tectonics could shift, carbon cycles could break, but for now, all of it continues. The rains fall, the oceans breathe, the planet spins under a sky held in place by the quiet tug of a distant moon. And Mars, circling nearby in its dry silence, watches. It does not warn us in words, but in presence. It is what a planet can become when systems fail to connect. It is what water looks like when it no longer cycles. It is the memory of what might have been, and perhaps what still could be in places yet unknown. If you have a glass of water nearby, on a nightstand, in a kettle, or steaming gently in a cup of tea, pause for a moment and imagine what that water has seen. Not the mug or the morning routine, but the molecules themselves. That single sip may carry hydrogen atoms more than 13 billion years old, forged in the early seconds after the Big Bang. The oxygen, likely born in the furnace of a long-dead star, met hydrogen somewhere in the cold dark of interstellar space, or perhaps during the violent birth of our solar system. Together, they formed the familiar H2O, the quiet architecture of all life, and began their long journey. Because water is a traveller, It moves through space, through stone, through clouds and bodies and time itself. It is not created or destroyed easily. The water we use, we borrow. It evaporates, it rains, it seeps into soil or flows toward the sea. It may freeze into a glacier, drift as vapour, or dissolve into blood. But it does not vanish. It cycles. It remembers. Some of the water now on Earth likely arrived from space, delivered by ancient asteroids and comets during the early bombardment periods. These icy bodies, flung inward by Jupiter's gravity, crashed into the young planet and released their cargo, not just rock, but volatiles, gases, water locked in crystal and clay. This foreign water merged with what Earth had already outgassed from its interior, vapour from volcanoes, hydrogen from minerals. The result was not a sudden sea, but a slow accumulation, a pooling of patience. Over billions of years this water has seen everything. It has passed through rivers carving canyons, through raindrops that fed ferns before the first dinosaurs walked. It lingered in swamps during the Carboniferous, rose in geysers from deep magma, and rested in trilobite eyes. When the great reptiles ruled the land, water circulated through their bodies, rose in their breath, and fell again with the thunder of their footsteps. And yet, it didn't end there. After the asteroids came, after the dinosaurs left, the water remained. It flowed into new creatures, birds, mammals, primates. It moved through them just as it moves through you now. The water in your body is mostly the same water that once filled ancient seas, floated as mist above woolly mammoths, and froze into the heart of a glacier that has since melted into a modern stream. In your blood, water carries oxygen from your lungs to your cells. In your brain, it cushions and communicates. Every heartbeat pulses with water. Every breath exhales moisture. You're not simply near water, you're of water. Around 60% of your body, by weight, is water, not in a stagnant pool, but in movement, constantly being absorbed, filtered, released. And when it leaves you, it doesn't disappear. It joins the clouds again, or the soil, or the sea. Water has passed through kings and commoners, whales and worms, the breath of glaciers, and the steam from fires long forgotten. It has slept in aquifers for centuries, then awakened in a spring with the silence of morning. It has circled the globe in storms and paused in teardrops on dusty cheeks. It has been everywhere and everything. This continuity, this unchanging essence through endless change, is part of water's magic. When you drink, when you bathe, when you listen to rain, you're touching something ancient. You're joining, momentarily, a molecule story that spans epochs. That same droplet may have once touched a fern in the Devonian, the tongue of a saber-tooth, the skin of an ancestor watching stars rise over a fire. The same water, new patterns, new vessels. This perspective invites a kind of humility. We tend to think of ourselves as separate, humans distinct from nature, each day a new start. But water does not honour those boundaries. It flows through kingdoms and generations without pause. It reminds us that nothing truly stands alone, and that everything we touch may have touched something else before and will again. Even now, as you listen, water is in motion. In the air around you, invisible but present. In your breath as you inhale and exhale. In the clouds passing above, the dew settling on rooftops, the distant rivers murmuring through valleys. It does not rest, it travels, sometimes quickly, spilled, boiled, evaporated, sometimes slowly, locked in ancient ice or held deep within a seed, but always, always it returns. If you were to trace the path of a single raindrop, not just where it falls, but where it has been and where it will go, you would begin to see that water does not simply move across the earth. It shapes it. It transforms mountains into sand, carries minerals across continents, and stores energy within clouds that drift for thousands of kilometers before releasing their weight. Every cycle of water is a kind of breath, a slow, planetary exhale and inhale that carves, nourishes, and sustains. When rain falls on stone, the story does not end at the splash. Over years, decades, or even centuries, that rain begins to break the stone down, not with violence, but with persistence. The tiniest cracks widen, grains loosen, minerals dissolve. Entire mountain ranges are slowly worn away by this patient force. Rivers form, fed by springs and snowmelt, and they begin their own work, carving valleys, meandering across plains, cutting canyons that tell the age of the earth in their layered walls. The Grand Canyon is not the result of some singular event, but of countless raindrops joining, flowing, whispering the rock into new shapes over eons. As these rivers move, they carry more than water. They lift soil, sand, silt, and minerals. They distribute nutrients across vast distances, feeding forests, wetlands, and coral reefs. They deposit sediment into deltas, forming new land where once there was only water. This movement sustains ecosystems and drives the chemical exchange between land and sea. But water does not only shape the surface, it works deep underground, seeping into porous rock, dissolving elements and transporting them silently through aquifers and underground streams. These hidden flows nourish roots and recharge springs, forming a vast invisible network that parallels the rivers we can see. They are part of the hydrologic cycle, yes, but they are also part of something deeper, a slower system of renewal that ties water to the rock cycle, to plate tectonics, and to the movement of the Earth itself. When oceanic plates slide beneath continental ones in subduction zones, they take with them not just basalt and sediment, but water, trapped in pores, in minerals, in sediments laid down by ancient seas. As this material descends into the mantle, it heats up, and the water is released. That water, even deep underground, plays a crucial role. It lowers the melting point of rock, enabling magma to form, and when that magma rises, it can erupt as lava or as volcanic gases that include, once again, water vapour. This process, known as the deep water cycle, is one of Earth's quietest engines. It connects the ocean to the mantle, the crust to the sky. Volcanic eruptions release not only carbon dioxide and sulfur, but steam, moisture drawn from ancient oceans and returned at last to the air. It is a cycle that spans hundreds of millions of years. A single drop of seawater that slips into a subduction zone might not return to the surface for 500 million years, and yet it will. Water, even buried, finds a way back, and as it returns, it helps balance the planet. When volcanoes release carbon dioxide into the atmosphere, water helps absorb it again. Rainfall reacts with silicate rocks in a process known as chemical weathering, drawing down CO2 and locking it into carbonate minerals. Over geologic timescales, this interaction becomes a powerful climate regulator. It prevents runaway warming, and after extreme cold spells like Snowball Earth, allows greenhouse gases to rebuild and thaw the planet once more. Everywhere water flows, it links cycles together. It connects the carbon cycle with the rock cycle. It supports biological cycles, circulating nutrients, transporting seeds, enabling the metabolism of every living cell. It does not simply move in circles, it forms circles within circles, nested cycles, each one reinforcing the stability of the others. On shorter timescales, water cycles through clouds and oceans, through rivers and lakes, through plants and people. But underneath that familiar rhythm lies this deeper, slower pulse, one that carries water through the planet's crust, drives tectonic movement, and helps maintain the balance of atmosphere and ocean over ages. It is not visible to the eye, but it is no less important than the rain that taps at your window, and through it all there is no waste. A molecule of water that helped cool magma in the deep crust may someday rise as mist from a morning forest. A drop that once dissolved limestone may later rest inside a leaf, or in the breath of a whale, or in the lungs of a child. It may be frozen for millennia, or evaporated in seconds, but it is always moving, always part of something greater than itself. This is what water does. It joins, it carries, it smooths and connects. It keeps systems from collapsing by moving between them, quietly ensuring that Earth's story does not end too soon. And the more we study it, not just where it is, but what it does, the more we see that water is not just a substance. It is a system of systems, a stabilizer, a messenger, a force that writes time into stone and memory into biology. So the next time you watch a stream curl around a bend or listen to the rain falling on trees, try to imagine the vast and ancient cycles within that moment. See not just droplets, but agents of balance. Feel not just wetness, but presence. Water is never idle. Even when it rests, it prepares to move again. If Earth has a rhythm, a gentle pulse that carries its story forward, then water is surely at its core. It moves not with precision like a metronome, but with breath-like patterns, slow, then sudden, hidden, then overwhelming, always moving forward, always circling back. Water is more than a compound. It is the heartbeat of a living world, pulsing through systems and seasons, rising through plants, falling as rain, washing away the old and carving space for the new. In the beginning, long before animals walked or forests whispered, it was water that first cradled life. Deep in the primordial oceans, warmed by volcanic vents or lit dimly near the surface, complex molecules gathered and reacted. Some dissolved, some collided, some bonded. Within the softness of liquid water, chemistry had the time and the space to become biology. The earliest life forms, tiny and fragile, relied on water not just to survive, but to exist. Cells formed with membranes that held water in. Inside those cells, water carried nutrients, allowed enzymes to fold and function, and create an environment where life could begin to make copies of itself. Even now, billions of years later, every living thing is a container of water. Trees lift it from soil to leaf. Whales swim in it and breathe it. Frogs sing after it falls. Birds trace its paths in the sky. You too are filled with it. It cushions your joints, carries your blood, surrounds your brain, and flows in and out of your lungs with each breath. You are, in every moment, part of the planet's water cycle. Not beside it, not watching it, but within it. But water's role in life is not only biological, it is emotional. It connects not just molecules, but memories. It gathers in childhood puddles, in riverside walks, in snowflakes that drift silently past windows. It holds the shape of grief in tears, of relief in a cool glass after thirst, of peace in the hush of falling rain. Even language reflects this deep bond. We speak of waves of feeling, of stillness like a lake, of turbulent thoughts and calm clarity. Water is metaphor because it is felt, not just seen. It is also one of the most unusual and elegant substances we know. Water expands when it freezes, unlike almost every other liquid. That single quirk allows ice to float, preserving life beneath frozen lakes and oceans. It absorbs heat slowly and releases it gradually, stabilizing climate and moderating seasons. It dissolves more substances than any other liquid, earning its title as the universal solvent. That ability means it can carry nutrients, shape landscapes, clean wounds, and etch patterns into glass and stone. It is soft enough to cradle, yet strong enough to cut through canyons. It is, in every way, a paradox, gentle but powerful, yielding but enduring. In the oceans, water continues to sustain life on a planetary scale. Tiny organisms, phytoplankton, float near the sunlit surface, photosynthesizing as trees do on land. These microscopic plants not only form the base of the marine food chain, they also produce a staggering portion of the oxygen we breathe. Every second breath you take likely comes from the sea. These organisms live and die in vast, unseen cycles, drifting with currents, blooming in springtime, and sinking into the deep. And through it all, water carries them, holds them, satters them, returns them to the dark. In forests and wetlands, in tundras and coral reefs, the story repeats. Water moves through root and stem, through cloud and cave, through animal and atmosphere. It creates the conditions for life, but also listens to life. It responds. More trees bring more rainfall. Melting glaciers alter ocean currents. Deforestation changes cloud patterns. The pulse of water is not separate from the planet's health. It is the signature of that health. When we say that water is the heartbeat of Earth, we mean that it connects everything. It binds stone to air, plant to animal, cloud to soil. It turns deserts into oases and carves silent paths beneath glaciers. And even when it disappears, when it evaporates into the sky or sinks into deep aquifers, it is not gone. It is only moving, waiting, preparing to return. And when we sleep, when the world grows quiet and the lights go out, water continues its work. It flows in the dark, down hillsides and across the ocean floor. It pools in low places and slips into cracks. It climbs through tree roots and hangs in mist above silent lakes. Even in stillness, it moves. That is why, even in the most desolate places, life looks for water. On Mars, we search ancient valleys and polar ice for its traces. On Europa and Enceladus, moons of gas giants, we hunt for buried oceans beneath icy crusts. Wherever there is water, we ask if there might also be life. Because the two are not just linked, they are mirrors. Earth, as we know it, is not Earth without water. It is the storyteller, the sculptor, the memory keeper. It holds the past, sustains the present, and shapes the future. It is in our blood and our sky. It flows through history and poetry, through glaciers and prayer. And even when we forget it, when we take it for granted, leave taps running, pollute its basins, it remembers us. It keeps moving. It waits in the air above cities, in the steam above a meal, in the quiet drip of a leaky faucet at night. It is the heartbeat of the world, and for now, it still beats. When you look at Earth from space, it glows in a way no other planet does. Wrapped in a soft blue halo, dotted with swirling clouds, looks less like a rock and more like something alive, breathing, turning, listening. This colour, that unmistakable blue, comes from water. Oceans stretching across continents, clouds trailing shadows over mountain ranges, ice catching the light at each pole, and yet that colour, the very signature of our planet, is the result of something profoundly unlikely. It is, in every way, a quiet miracle. For all the physics, all the chemistry, all the careful layering of systems that came together to hold this world in balance, there is still something else. Luck. Earth had the right size to keep its internal heat, the right distance from the sun to stay warm but not boil, the right gravitational companions to receive and hold water without being destroyed. It kept its magnetic fields spinning, its volcanoes breathing, its carbon cycling, and all of that, every scent, invisible feature, worked together to let oceans stay, to let rain fall, to let rivers continue carving their way across the land for billions of years. Mars was not so lucky. It formed from the same dust, circled the same star, and yet its story unfolded differently. It cooled too fast. Its magnetic field collapsed too early, and its atmosphere slipped away, molecule by molecule, into the endless dark. Water once moved across its surface too. We've seen the evidence etched into stony river channels, sediment fans, the faint suggestion of ancient lakes. But without a sky thick enough to keep it warm, or a shield strong enough to hold that sky in place, Mars couldn't hold on. Its story diverged, quietly until it became the dry, rust-red world we know today. And it's this contrast, not of violence but of fragility, that makes Earth's oceans feel so precious. We often take them for granted, these vast bodies of water that move with the moon, that hold the memory of winds and the songs of whales. But they could so easily have not been. A few different choices in the early solar system, a few different nudges from Jupiter or tilts in Earth's rotation, and our planet might have been silent too. Cold, still, blue only in the imagination. Instead, Earth chose breath, chose cycle, chose movement. Or rather, it had the right conditions to allow those things to persist. And because of that, we live on a planet where clouds gather over forests, where waves polish shorelines, where lakes freeze and thaw and reflect the stars. All of it. The soft murmuring of a stream, the roar of rain on rooftops, the hush of fog at dawn, rests on this single, shared gift. The comparison to Mars reminds us that nothing is inevitable, that life is not the default, but the exception, that water is not always present, even when the conditions seem close. It takes more than just temperature and distance. It takes 1,000 invisible balances, each one nudging the next, each one holding the line so that water can remain liquid, can remain moving, can remain part of the story. And yet, in that contrast, there is not sadness, only reverence. Mars did not fail. It simply walked a different path, one that reveals, through its stillness, how much movement means, one that, by its dryness, teaches us to feel the weight of a raindrop more deeply. Mars holds up a mirror to Earth, not to reflect what we are, but to remind us what we might not have been. It shows us that habitability is not a guarantee, not a universal rule, but a delicate harmony of factors that, for reasons we are still learning to understand, manage to come together, here, on this blue and breathing world. When we gaze at Mars, what we see is not just the absence of water, but the absence of a chance. A planet paused before the crescendo. It is a place that almost had rivers, clouds, maybe even life, and though its silence seems final, its memory remains written in its valleys, its dry deltas, and its thin air. Mars tells a cautionary tale, yes, but it also deepens our gratitude. Because in comparing two planets that were once so alike, we see how every drop we hold, every wave that reaches the shore is not just a feature of Earth, it is a triumph of Earth. This gentle comparison reminds us that the same solar system can produce two destinies, one warm, wet, and rich with stories, the other dry, cold, and haunting in its quiet. It's not just a matter of luck, it's the way the universe balances complexity. And Earth, for all its storms and sorrows, for all its shifting continents and occasional upheavals, still holds its water close, still cycles it through cloud and root and bloodstream. So the next time you hear the sound of running water, whether it's the splash of a sink, the trickle of a stream, or the rain tapping gently on glass, you might remember Mars, not with pity, but with perspective. You might pause, not in fear, but in wonder, and you might feel, even for a moment, what a rare and generous thing it is to live on a planet that still sings. Now, as the journey gently draws to a close, you might feel the presence of water, not just as a concept, but as a companion. It has followed us from the beginning, through the first clouds and oceans, through collisions and comet dust, through tectonic breath and rivers of time. It has been the quiet thread running through everything, through the landscapes we've studied and the stories we've uncovered, through Mars' memory and Earth's resilience, through science and stillness alike. And it continues to follow you now, here in this quiet moment. It's in the breath you've just taken, it's in the glass on your table, in the soft hum of a kettle, or the silent weight of clouds outside your window. And every time you sip from that glass, every time you touch the coolness of water or listen to it fall, you are not only engaging with something simple, you're touching something ancient. You're connecting to a molecule that may have circled the globe 100 times, that may have drifted in a dinosaur's breath, or been locked in a glacier for millennia before returning to you. There is wonder in that, if you let it settle gently in your thoughts. The cup of water beside you is not just refreshment, it is history. It is cosmic. Hydrogen forged in the early universe. Oxygen born in stars. The two joined in the vast cold of space or in the deep churn of Earth's early crust. And now, here it is, shaped into a sip, a droplet, a presence. Its story momentarily continues with you. That is the beautiful part of being human. We do not simply exist within the universe. We feel it. We carry meaning with us, wrap it around science like a blanket, make constellations out of patterns and lullabies out of knowledge. The stars burn, the water flows, the planets turn whether we notice or not. But when we do notice, when we pause, listen, reflect, we turn motion into memory. We turn cycles into significance. So much of water's story is movement. Yet in this moment, you're allowed to be still. There is no rush. The oceans continue their tides. The clouds will move, the rains will come, whether you're awake or dreaming. The systems are in motion, but you just now are held. And perhaps that's the greatest gift of all, to live on a planet where you can fall asleep without worry that the air will vanish or the seas will fade. To sleep under a sky that breathes, on land shaped by water's gentle insistence, with lungs filled by an ancient ocean's whisper. So tonight, or whenever you hear these words, let that thought be enough. Let it be a soft exhale, a quiet recognition that, despite all the chaos in the world, despite the noise and the uncertainty and the speed, the seas still sing, the rain still falls, the world, for all its flaws and frailty, still turns in rhythm with water's heartbeat. And you, who carry water in every cell, who breathe it, drink it, and are shaped by it, are part of that rhythm too. So sleep now, if sleep is near. Let your breath slow, let your thoughts drift, like mist rising from a forest floor. There is nothing more you need to hold tonight. The science will be here in the morning. The stars will wait. The molecules will continue their dance through time, and the water will remain.